but I did want to. Okay, now I'll go back to. Sorry, folks, I forgot to turn on the sound, so a while there we didn't record, but nothing new. This is pretty much where we left off last time. All right, so here's the end of your massive stars. Now, there's a few things I sort of find a little irritating about the way they put these slides together, but it's also in the book, and it just does some strange things here, but I'll explain that later. Okay, so the more mass, the more gravitational contraction and heating you have. Now this is picking up pretty much, let's go back to the last slide. Wrong way. Okay. Where the core is collapsing, heating up, and helium is fusing to carbon, radius and luminosity decrease, moves back toward the main sequence. Okay? That's kind of where we are with the more massive stars, but the more the mass, the more the gravitational collapse, and the greater heating you have. Okay? Now, here's a critical temperature. If there's enough mass to heat to as much as, I can't even imagine this, 600 million K, okay? That is hot, okay? Like I said, there's no one's determined that there is a maximum temperature. There is a minimum temperature, absolute zero, but there is no known maximum temperature. If it goes that high, now, rather than becoming a white dwarf, carbon that just fizzles on out, now you have carbon fusing to heavier and heavier elements, okay? The heavier nuclei fuse, and they keep fusing up until you get to iron. Now, there's something about iron on the periodic table that it doesn't naturally fuse past iron. And if you go back, if you have a big book, most of you don't, you have the little books, okay? Go down to the bookstore and see if they have the big books, or see if they have part 2 in there, which is actually part 1 of this book. This is Science 2. Look through that chapter on nuclear, and you'll see there's a graph and why iron is the last one it naturally goes to, up to iron. Now here's iron on the periodic table. Remember, we had hydrogen fusing to helium, helium fusing to carbon, carbon fusing to other things until it gets up to iron. At iron, the naturally occurring fusion stops. It gets up to iron. Now, later we're going to be talking about planets. This is the next chapter. And we'll find that most of the planets have, guess what, an iron core. That may be why, because this is where the fusion stops. Our Earth, most of the core of the Earth is molten iron. Some magnesium, some nickel, but mostly iron. The little bits of iron that make their way to the surface, that's what we mine as iron ore, okay? Birmingham, Bessemer area, they've done a lot of that in the past, okay? But fuses up to iron. Now, all the fusion energy sources are now used up. The energy expansion, with the energy expansion, now fusion is what's blowing out, but if there's any collapsing that's going on, the energy expansion is, pressure is lost, the dynamic equilibrium is disrupted, what's going to happen? Now, this is where I get a little irritated. They started with the less massive star, and now they're going to go to the most massive star, and then they're going to come back to the medium massive star. So I don't know why they do this, but every table they have, they show up in this order. Okay, so let's go to I think this is the most massive star. The supernova occurs. Okay, the star collapses because there is no more fusion going on, no more blowing out. That dynamic equilibrium is disrupted, and it starts collapsing on itself again. You remember what happens like that? It starts heating up as it collapses. Not enough to do any more fusion. All the fusion's through, and it sort of collapses on itself and then blows up. Okay? Rebounds from the core. Now, that collapsing actually, in a sense, does do some more fusion. Okay? It's not the regular fusion that we had here. In a sense, it's sort of like that, but this is where the heavier elements come into play. Elements beyond iron are created in this massive explosion that happens because it literally does force other molecules or atoms together, but not enough to sustain itself. No more dynamic equilibrium, that kind of stuff. So you do form these heavier elements. Okay? That's where all these things, there's iron right there, and all the ones below iron are formed there. But if you look at this, try to find these things, very rare. There's where some of your precious metals are. Silver, gold, mercury's there, platinum's there, all these things that are very rare to find. These are called the rare earths. You know, they are very rare compared to iron and the things above it. Okay? So that's why there's not that many of them. They are formed, created in the explosion, distributed throughout the universe, and that's why we found them on Earth and other places as well. All right. Now, this is, okay, I'll take this back. This is for all the big stars. Okay? The ones too big to just become a mass of carbon, that you have this. Subsequent events depend on the mass of the remaining core. So all you got left is the core. You've blown everything else away, and that's what's called the supernova. It's blown away. So all you have left is the core. Okay? So here is where they do it. Now, if the remaining core is between 1.4 and 3.0 solar masses, that's about 1.5 to 3 times the mass of the sun. Now you say, hey, that's not that much bigger. Wait a minute, this is just the remaining core. You've blown away most of the original mass, okay? This is just the remaining core, and it's still 1.5 to 3 times the mass of our entire sun, okay? The gravitational pressure fuses the protons and electrons into neutrons. This is where neutrons come from. Rather than fusing atoms, now you're fusing the components of atoms, and you fuse the protons and electrons into neutrons. And sure enough, if you were to go back and read some of the nuclear chapters, you'll see that the mass of a neutron is just slightly more than the mass of a proton. Not much. Hardly noticeable, but it is measurable. What's the difference? Almost the mass of an electron. Okay? And you see an electron is negatively charged, a proton is positively charged, fused together, 0 charge. That's where neutrons come from. Okay? Now, if you're just that size, 1.4 to 3 solar masses, this is what you become, a neutron star. Now, what is it about neutrons? Remember, no charge. So there is absolutely no tendency to do anything but collapse on itself. There's no repulsion, there's no attraction, it just so these are incredibly dense stars. Okay? And there's something about neutrons, and I can't explain this at all. I'd love to see an explanation of it. You probably get some type of Nobel Prize for Physics or something if you could come up with one. But why does this neutral spinning star out there pulse? Okay? But they do. This is called a pulsar. a pulsing star, okay? It's rotating and it's magnetized. Now that's the part I can't understand, because magnetic fields come from moving charges. A neutron star is neutral. What is creating the magnetic field there? I don't know. Now maybe some physicist somewhere out there does know or have a theory about it, but it is a rotating magnetized neutron star. Because it's rotating and it's magnetized and probably not sitting perfectly upright, then when the pole comes around, you get a pulse, and then it dies, and then it pulses and it dies. So that's a pulsing star. It's called a pulsar. By the way, the first pulsar, I believe I'm right on this, ever discovered was by a woman working in one of the big astronomical labs somewhere. And if I'm not mistaken, I may be getting my stories crossed up, she was a grad student at the time. So when they went to award the Nobel Prizes for discovering this star, her bosses got the Nobel Prize because they only give Nobel Prizes to the PhDs, not to the persons who found it. So they gave them to, and everybody that was any sense whatsoever was up in arms about that. Wait a minute, her name should be included, okay? Include the honchos, but her name should be, no, you won't do that. You know, and it was mostly just sexism, okay? I don't believe it was any hard and fast rule that they had to go by. It was just that. Irritated, her bosses were furious, okay? If I've got the story right, I believe that's the one. I know that happened. I think that was this situation here.
What was her name?
Second?
Do we know her name?
Okay.
Do we know her name?
Yeah, I'm going to give it.
Okay.
I can't remember right now. It's Burrell. Susan, she has like 4 names. I can't remember them all. I'll talk about them a little later. Okay. Now, that's your less massive of the more massive stars, if that makes any sense. Your really massive stars, those whose remaining core is greater than the 3 solar masses. Now, there's nothing special about 3 solar masses. It's just something we can at least sort of have an idea about. But those that are beyond that, their gravitational collapse overwhelms all known forces. Yes?
Quick question.
Sure.
Projectors, what 3 rooms are your highest priority?
Okay, wait. Let me.
Can you just text that to Dr. Davis shortly?
I'm going to be in class till 5:45. These most massive of stars, greater than 3 solar masses, remaining in just the core now, this gravitational collapse is stronger than the gravitational collapse that fuses protons and neutrons and electrons to make neutrons. This overwhelms all. Oh yeah, somebody else came in. I'm sorry. There were too many things happening at once. What's your name, please? Okay. What do you go by, Maurice? Okay. All right. This is your first time here, right? Okay. Has anyone else come in since the called roll? Okay. Oh, I got you, I think. I knew who you were. I had eyes on you. Okay, never mind. Okay. Chris is still not here, right? Edward, Jemiah, and Tarika. Okay. Everybody else is accounted for. Okay. Now, sorry, time out, folks. Let me catch up, Maurice, with where we are and what we're doing. Okay, we've already started. Okay. Last time, we've got 4.5 hours to spend. Last time we went over the syllabus. It's not on Blackboard yet. Hopefully I'll get it there someday soon. The research paper topic, it'll be there. Oh, and by the way, I record everything that we do. Did I turn this back on? Yes, I did. Okay. You're supposed to be watching for that. I'm sure I did. Okay. So as soon as I get the link done, you can access what we did last time. Okay. You go to Blackboard. When you go in Blackboard, there will be, in this class, there will be a series of tabs here. They go, scroll down for pages. They come in groups, I don't know, 5, 6, 7, 8 or something per group. Somewhere in that first group is one that says it says course information. That's where I put the syllabus. It's not there yet, but I'm going to get it corrected and put it there. Then right under that is instructor information. Nothing's there yet, but I'll put my locator card there, showing when I'm on campus, off campus, in class, out of class. Then the next group is one that says something like class handouts, PowerPoints, and more, something like that. That's where I will put, it's not there yet, the research paper instructions, all the PowerPoints that we'll possibly do in this course, a few websites that students have sent me in the past that they found interesting and I found interesting, some pictures from the Hubble Space Telescope, just some really neat little stuff like that, nothing too important, but just really good stuff. And then somewhere in that will be, it says, Physical Science or PHS112 YouTube videos. It's not there yet, but when I get it there, then you'll be able to pull up and see. Now, let me explain those YouTube videos. I may not have done this for the rest of you, but let me do it now. I leave, what's in there now is every video, a video on everything I've covered before in some class, probably the last time I taught them, okay? And I leave them there until I do it again this term, then I delete the previous one. The reason I do that, did I go over this before with y'all?
Mm-hmm.
I did, okay. It's because sometimes the systems fail. And if I can't record something, I'll leave up what I did the last time I taught the course. So it'll always be somewhat continuous. Maybe not in the same order, but it's there. So as soon as I get the link, you'll be able to see what we have done this time. The older ones are at the top, the newer ones are at the bottom. Right now there's only one that's at the bottom there, but you can't access it anyway. After today, there'll be a second. Okay? So you'll be able to go and see and hear everything that we did last time. And everything on there you're responsible for. Okay, so go listen to that. I'm sorry, 4.5 hours of blah, blah, blah. Okay, good. You got the idea. All right. And we're well underway into chapter 1. We'll probably finish, chapter 14. Probably finish 14 today, start on 15, and have the lab for 14 the last 2 hours today. All right. So let's get back to this most massive of stars, more than 3 solar masses here, collapsing on themselves, going beyond just pushing protons into electrons and making neutrons. You are actually overwhelming all known forces. Everything we know. Even light cannot escape from these dense, compact objects. And this is what we call black holes. Okay? We have no clue of how they operate. It's forces beyond what we have any perception of. We just know that anything that gets close gets sucked in. And we don't know what happens to it. But it's concept beyond what any of us, our brightest scientists, can't quite figure out. There's lots of theories, but they're all over the place of where this stuff goes. So that's the ultimate destination of your most massive stars. The ones before that became neutron stars, and they don't really shine, but they pulse, and you can detect them. These things don't do anything that we know of. The only reason we know they're there is other things will pass in front, and you see them, and pass behind, and you don't. Okay? The light doesn't make its way through. So we know they're there, but we don't. And they can detect masses, and they are incredibly massive. Okay? Incredibly dense. Okay. This is the diagram I was talking about. That sort of shows the whole picture here. We're starting with the massive gases, the nebula, okay? Huge, taking an enormous volume. I mean, more than solar system size volumes, okay? Just huge volumes of gas out there. Where did it come from? Probably stars that have already exploded in the center of gas there, and they sort of hang around in close proximity. Something happens, some sort of pulse happens that forces some of them closer to each other, and when it does, they stick. And now they start building up gravitational attraction, and they start pulling in more and more and more. So you go back and read. Ultimately, if there's enough of it, and it's hot enough, you get to the protostar. That's the thing that once it passes this stage, it's going to become a star. These masses of gases won't necessarily ever become a star unless something happens that gets it to that stage. The protostar, that means it's past the point of no return. Cross the Rubicon, okay? It's got to the place where it's going to become a star. Not there yet, but it's okay. That's when your fusion starts happening and you're trying to set up the dynamic equilibrium and stuff. But then, when it finally becomes a star, it's in the main sequence. Okay? Now, this is the diagram that I find confusing, and yet it's in the newer edition just like this. Let's start with the low-mass stars. It remains in main sequence for its lifetime. Now, the low-mass stars, they could be trillions of years or billions of years. It's there in the main sequence. Okay? But when it finally uses up all the hydrogen, fuses it all into helium, then you have the beginning of the end. No more outward pressure, so gravitational comes back into play, but that is forcing a lot of heat, and the heat is expanding the outer shell out, so it becomes a red giant. It was just a little old main sequence star, now suddenly it's a red giant. Giant because it's big, red because it's cooler. Okay? Now get your name, please.
Me.
Second. McNicken, got it, okay. I'm hard of hearing. There we go. Edward, right? All right, good deal. Okay, so now it's become a red giant. You can see it better, okay, because it's so big. Still emitting light, but not white light or yellow light or whatever light it was. It's now a red giant. But when it then collapses, forming the helium collapsing and fusing into carbon, and that's its last hurrah, and blows up, and that would form a nova. They don't mention that here, and that becomes ultimately a white dwarf. When the white dwarf finally cools, it's just a cold lump of carbon. Okay? We don't know whether it's diamonds or just lumps of carbon, but it's one of those because carbon is diamond. Okay. The mid-mass stars, and maybe that's us, okay? The only difference is it's a bigger red giant, okay? And when it blows that last time, it indicates here this red giant just collapses on itself and makes it a white dwarf. I imagine it has a little bit, but not as noticeable a planetary nebula. And the white dwarf will be somewhere in the center and the gas is blowing away. It becomes a white dwarf just like this one and ultimately cools and becomes a cold lump of carbon. All right, now this is the part that I found. Why do they do it this way? It seems like to me for the high mass stars, this is true, these are what we call the supergiants. You remember back on the Hertzsprung-Russell diagram. Here was the main sequence stars, here were the white dwarfs, here were the giants, and here's the supergiants. Okay. This super red giant is up here. When it goes through its collapse, there is a supernova. These you might consider sort of a little nova, supernova, and this is basically comes after you have, or about the time you're fusing carbon into the bigger elements up to iron. And when the supernova happens, then more fuse and become the heavier elements as well. I think there is a supernova somewhere out there that astronomers are paying a lot of attention to. It's a long, long, long way away, but with the most powerful telescopes, it may take Hubble or something like that to see it, but they have been very interested in that because you don't get to see them all the time. And I think there is one out there. You can read up on that. It might be a good paper topic, somebody. Okay? Okay, think on that. Now, here's the part I don't understand. This was low mass, mid mass, and then they put less massive than the most massive stars, and then the most massive. Why didn't they reverse these two? I don't know. But to me, these should be swapped, and the neutron stars come next, because that's when the high mass, but not high enough mass, fuses and becomes a neutron star. Okay? And those hang around and pulse for quite a while. Okay? The most massive stars become your black holes. Okay? That's the end product. They both supernova, but this one finally collapses on a neutron star. This collapses, but we don't know why. Okay? Nothing is coming out of it, not even radiation. So that's why it's so hard to detect, because there's nothing coming out of it. This is emitting magnetic pulses, okay? This is emitting nothing at all, sucking in everything it can. All right, so there's your black holes. Now, every galaxy that I know of, I don't know that many, but everyone has a massive black hole in the center. So your smaller galaxies probably have less massive black holes, but they have them. And some of even the star clusters may have a small black hole somewhere in the center of those. We'll talk about those things a little bit later, but anytime you see a galaxy, somewhere in there is a black hole. Okay. Whoops, too much. All right. That ends our discussion of stars, pretty much. Okay? Let me go over and just see if there are any things. There's some pretty pictures in the text. One is I believe one of the pictures very similar to the one you see that you will see, it's not there yet, from the Hubble telescope. Then at the top of page 364, Observing New Technology. It's pretty interesting to read about. You're not going to be responsible for it, but it may give someone a good idea of a paper topic.
What page was it?
Top of page 364, Observing with New Technology. It's just describing some of the different ways we look at stars. Just to mention a few.
No, it's not testable, but you can get my head.
Yeah, it may be a good idea for a paper topic or just of interest to you. An X-ray telescope isn't capturing light, it's capturing X-rays. And that will tell you something that light won't necessarily tell you. Okay? Infrared telescope, that's not capturing light, it's capturing heat that's put off. Lower X-rays are higher energy than visible light, whereas infrared is lower energy than visible light. So they're looking at the whole spectrum with different types of things. There's gamma ray telescopes, which are the very highest energy, much higher than X-ray telescopes. And they have what they call radio telescopes, which measures radio waves. Those are even lower energy, longer wavelength waves than infrared. And so they just mention several of these and tell you some of the things there, the names of some of them, when they went up, and what they've been finding out from them. Just sort of an interest thing. All right. So now, okay. Something we talked about very early, light pollution. Anyone living anywhere near the towns, cities, things like this, terribly, you can't see many stars. The reason is there's so much light out there, it bleaches out the stars. Now, Ruben here told me after class last time, he was in the Navy also. I was in the Navy. When you're out there on a ship in the middle of the ocean by yourself, there's not much light around. Okay, none whatsoever. And boy, can you see the stars. Okay? And so if you ever get the opportunity, there's some places in the planet. I heard on the radio just recently, one in either Washington State, way east in Washington State, or somewhere in Utah, somewhere out there, there's just a fantastic place for making observations of dark skies, because there's no towns anywhere close. And those areas have built up sort of a science mecca, and they do their business, but they keep the lights off. Okay, so there are places you can go and see that. All right, so there's a blurb there on Science and Society, light pollution. Okay. There is a picture on page 365 of someone looking at a portion of the Milky Way. Most of us will not see the Milky Way on our night skies because of light pollution. But if you get out in the boonies, way away from it, you'll see, on a clear night, you'll see that. Spilt milk is why they call it Milky Ways. And that's what leads to what we're talking here. The larger scale structures. Now, if you may have thought the stars are the basic units of the universe, they don't count on that. Those are the little pieces. Planets are next to nothing. Okay, moons and asteroids, dust, you know. But the larger scale structures, let's start with stars. You have binary systems. These are two gravitationally bound stars together. They rotate around each other. Okay, those are called binary systems. Two stars gravitationally bound together. Most stars, surprising to me, are binary in pairs, not singular stars. And guess what? Our sun is one place where it's not average. Okay? It's a unitary star, which puts it on the rare end of things. Ours is not a binary star. Most of them are. Most of those stars you happen to see are going to be binary or more than one star. Ours is one of the few that are rare ones that are single stars. Which leads me, this is sort of an aside here, leads me to think it's going to be a lot harder to find life that can exist in a planet going around a binary star. Or it seems that way anyway, because that binary star, sometimes you're hot, and sometimes you're not quite as hot and stuff, because you've got more or less radiation as you make your orbit. Can life exist in that big a fluctuation? Not life as we know it. Maybe some other life form can, but not life as we know it. And then when you consider what we talked about before, how valuable our atmosphere is to block out those harmful radiation and give us only the white light that we need to reduce photosynthesis in trees, man, it's a very delicate little system. Which then leads me to think, what are we doing with this delicate little system by pumping all the extra carbon we're doing into, there's some bad things happening now. How much can we do before we tip the balance to irreversible decay? That's scary. Okay. Now, even bigger than binary systems are star clusters. Now, this statement here is hard to interpret for me. Are they saying tens, like 10s, 20, 30, 40, up to hundreds of thousands? Or are they saying tens of thousands up to hundreds of thousands? It's hard to tell from this. Read the text, see what you think. They almost are as vague in that. But these are much bigger systems than binary, okay? Tens to hundreds of thousands or more gravitationally bound stars that hang around together. They may be within a galaxy, or they may be outside of a galaxy. Now, if they're hanging around together, there's a good chance there's a little black hole somewhere in there that's pulling them together. I can't say it's always, but they often share a common origin. For instance, that mass of gases that you saw in the previous slide, it was so big that it formed, and then maybe later another one formed, but they all came from that same mass of gases. So it may be several stars, or thousands of stars came out of that. Okay? But then, we get to the big classes, and these are the galaxies. This is the basic unit of the universe. not stars, certainly not planets or asteroids or meteors or anything else. The basic unit is the galaxy. What are galaxies made up of? Billions and billions of gravitationally bound stars. Guaranteed that gravity is coming from an enormous black hole somewhere at the center of that galaxy. Okay? And pulling everything around it. Okay? Billions and billions of gravitationally bound stars. Now here's the scary part. There are billions and billions of galaxies out there we know of, and probably billions and billions we don't know of. So the numbers are astronomical. Okay. Larger scale still, you have clusters of galaxies. Okay? Wow. And then superclusters of galaxies. Wow, and billions of those galaxies. I got ahead of myself there. What are we? That anyone is mindful of us, okay? We are a little speck of dust. Less than a little speck of dust in an enormous universe. I mean, it's just amazing. Okay? And I'm talking about the planet. We're less than ants on the speck of dust. Mites. Okay. And yet someone cares. All right, let's talk about a little more specific, our galaxy. And by the way, we're getting almost more extra stuff than we are text here. On page 366, there is a blurb on a closer look. It's called Extraterrestrials. Now, y'all are probably too young to remember E.T., right? Oh, some of you remember E.T. Okay, good. That stood for extraterrestrials, okay? Obviously, science fiction, with the emphasis on the fiction part, though there may be a little science in there. Read this. In order to move from object to object, like they said here, they have a little thing here. There is nothing special or unusual about the sun. Astronomers believe it to be quite ordinary among all the other stars. And they list a number here with a 3 and 1, 2, 3, 4, 5, 6, 7 sets of 3 zeros following that 3. So I don't even know what number that is. Okay. And if someone were to travel from some other place to here, it would literally take generations to make that. Not a single person leaving some other place. No lifespan is that long. Okay? Nowhere close. Okay? So lots of big numbers in this. Read that. It's pretty interesting. So let's move on to Milky Way galaxy. Okay? If you get out in the boonies somewhere where there is no major light pollution, and you look up on a very clear night, not much cloud or anything else, and look up, you will see among all the very bright stars that you've never seen before, you'll see this mass of very diffuse light. And that's part of our galaxy. It's billions of stars, The Milky Way is visible as a diffuse band on a very dark night when you are out in the boonies, okay? The Milky Way is made up of literally billions of stars. Now, some of these are found, I think they mean here, star clusters. I think that word is incorrect here. If it was galactic cluster, the Milky Way would be in it. But I think they mean star clusters here. So what is the structure of our galaxy, the Milky Way? There is a giant galactic nucleus. Now, I can't even begin to guess. Okay, here's a good picture of the Milky Way taken from somewhere way out in the boonies, probably very, very high, so you have less atmosphere to do it. Boy, anyone ever ever say it looked that clear? No, I haven't either. And I lived out in the country, way out in the country. And this is maybe time for another dumb story. Sorry about this. I shouldn't take up time for it. But I went to Georgia Tech. Okay, Georgia Tech has a hard time keeping 50% of the population of the college from the state of Georgia because it brings in students from all over the country and all over the world. It's a really good school, a really hard school. And when I was a freshman, I lived in the freshman dorm. When I was a sophomore, I got a job in the freshman dorm as a student counselor. And they call them resident assistants everywhere else. At Georgia Tech, they call them student counselors. And then I became a senior counselor in that same freshman dorm, and then ultimately became a resident advisor my senior year. But back up a bit, when I was a senior counselor, there were a couple guys that moved up on the third floor in the place I used to be the counselor, and they were pretty much from one's from Boston, one's from New York. Bob and Max. Max from Boston, Bob from New York City. And nice guys. And then the next year, I was still in there the fall term. My younger brother was a freshman. And he lived up on that same hall. And Bob and Max had stayed up there. And he got to know them, pretty good friends with them. And since they were so far away, they never got to go home. So he said, why don't you come home with me one weekend? Well, I usually had to work all during the weekend, so they took off in my car, because he didn't have a car on campus, and drove to the farm. And the farm, like I said, is out in the boonies. I used to say we're 7 miles from the closest flashing yellow light and 10 miles from the closest red, green, and yellow stoplight. That's how far we were from any civilization. Okay? And Dan took them over to my grandmother's house. She was in failing health, so she was living with my mom and dad across the street. I can't imagine why they were there in her house by themselves, college students, away from the parents and grandparents. I don't know what they were doing for sure. I can guess. But it was a clear night, and it was, I think, early spring. And because I think the soybeans were just coming up in the field. And they happened to go outside, and Bob and Max literally just went running through the field screaming. They had never seen that many stars in their lives, anywhere close to it, because we were way away from light pollution. New York City, Boston, Atlanta, no, not a chance. And Dan was just there laughing his head off at them because they were absolutely nuts. Whether anything was making that a little more acute, I don't know. We won't get into that, but they were incredible. And I bet you that night you could have seen a little bit of the Milky Way. Probably not that bright, but a little bit of the Milky Way. Okay? And that's and I think this is also magnified because they've taken through a telescope too. So that's why it's a little brighter. Now, here's a guess of mine. This is probably one of those star clusters, and that's probably a star cluster, or else it's a reflection on the telescope, I don't know. This is probably a star cluster, okay? It's just a lot brighter than the rest of them, okay? Now, what you can't see is what they're describing here, so let's go to the next slide. And this is what our idea of what the Milky Way looks like. We've never gotten far enough away that we can take a picture of it, for sure, okay? But this is what we think it's like. Anyone know why we can model it like this? Has anyone ever heard of Andromeda? What is it?
A neighboring galaxy.
Say again?
A neighboring galaxy.
Yes, you're absolutely right. It's the next closest major galaxy to us. We're called sister galaxies. It's probably a little bit bigger than we are, but this is how it looks. We've seen it through the Hubble Space Telescope and other places, and we know that it looks like this, and there's all indications, because of how the Milky Way looks in our sky, that that's probably what we look like too. Okay? So, in the middle of this is a galactic nucleus. Okay? This is looking from the top, this is looking from the side. Okay, you take this, rotate it like this, and there's your galactic nucleus there. Okay? I don't know how dense those stars are. They seem like they're awfully close together. They're still astronomical distances from each other. I mean, even though it looks like they're awfully close, they're still incredibly far apart, even in this cluster. Okay? Now, there's a rotating galactic disk. That's what you're seeing here. This is the disk here. Now, again, people who are listening at home, you can't see the this and that I'm pointing at. Sorry about that. I guess perhaps I could be doing this, okay? There is the nucleus, there and there. Here is the disk looking from above. Here is the disk looking from the side. We know this because we see the Andromeda, and we think we're shaped a lot like that. Okay, here is where we are. Way out, not at the edge, but way out. Okay? Now, I don't know this for a fact, but I'm pretty sure about it. Do you think there's anywhere in there that could be the galactic nucleus? Maybe this bigger portion here? I doubt it. Here's what I'm guessing we're seeing there. Okay? When we hear somewhere in this spiral that comes out of that rotating galactic disk, we're looking back. Here we are. What we see when we look at the Milky Way is when we look this way or this way. Okay? We're not seeing anything close to that. Everything else we see, this stuff here and this stuff here, this is what we're seeing on either side, in between. We're not even seeing this next band over here. We're just seeing the stars along in here. This is such a massive thing. We're not seeing any of the other stuff. Okay? This rotating galactic disk, the diameter is about 100,000 light years diameter across the thing. From here to here, from there to there. 100,000 light years. Now, if you remember what a light year was, how many zeros were after the first after the first digit there? I don't know, 15, 18, 20, and now multiply that by another 100,000, and that's how big the Milky Way is. So going back to that, could we talk with an extraterrestrial? Well, guess what, team? To get just to the next little star from us, you're talking about hundreds or thousands of light years, okay? Not hundreds of thousands, 100,000, but hundreds or thousands light years. So if we said, "Hi, Centaurus, how are you doing?" In another 100,000 years, they'd say, "Fine, how about you?" But it'd take us another 1,000 years or so, 100 years or so to hear the answer, okay? No, not going to happen. Now that's traveling at the speed, if we sent that in a radio message, that's how long it would take. If you were traveling in a vehicle, you'll multiply that by enormous amount. So yeah, the chance of an extraterrestrial, pretty slim, okay? Now, so that's the rotating disk. There's also this spherical galactic halo, okay? And that's what this is, okay? A spherical galactic halo that's all around that disk, okay? There are globular clusters out here, star clusters, globular clusters out here outside the disk, but still gravitationally held by that center. And in the center of that nucleus, somewhere in there, is your black hole. Or maybe a few of them, I don't know. Okay. So the spherical galactic halo contains probably 150 of these globular clusters. This just shows a few of them in 2 dimensions. This is 3-dimensional, so it's incredible. Now, somewhere, I can't remember where it is, it talks about the fact that Andromeda and Milky Way may be on some sort of collision course in sometime in the way distant future, and that they are coming closer to each other. Now, this doesn't make sense compared to something we're going to read in just a little bit, okay? But I've heard and read this too. There is such distances between the stars and everything in it that more than likely, if they did happen, this is what happens. Nothing ever collides. It just, they go right through each other because there's way more space between than there's matter in between. Goodness gracious, you're talking huge amounts. To see stars that look that bright and look close together, and they're nowhere close to each other. Not any 2 of them, except those that are binary pairs or star clusters. All right, so let's move on to, and before we leave this page, here's her name, Jocelyn Susan Bell Burnell. Okay, she was born in 1943. At the time of the printing of this book, she was still alive. I don't know if she still is now. She identified many of them. Okay, I can't remember how many, but she was well worth a read. Now, remember on your papers, if someone chooses to write on her, there's a lot of information here, but this is off limits. The book cannot be your source. You need to get outside the book and find the information on her. It may be some of the same information, but it has to be from another source. Okay? You'll hear that when I talk about the paper topics. Okay. All right. She was the first to find these pulsars, a pulsar. Okay. And I believe she's the one that whole deal of the Nobel Prize, that fiasco. So let's look at other galaxies now. Our nearest neighbors, there's one thing called a local group. The local group are some dwarf galaxies that are hanging around there, probably smaller black holes, you might say, or something like that. These are about 1,000 light years in diameter. So less of around 1/100th of the size of the Milky Way. Minuscule, right? Okay. No, really huge still. The nearest dwarf is being disrupted gravitationally by the Milky Way. That's not going to be something that just passes through. It's so small, the Milky Way is basically sucking it in. You may not get it all, but it looks like it's disrupting that galaxy, and it's going to probably tag along some of the outer fringes of the Milky Way sometime in the future. The next major galaxy is Andromeda. It's 2 million light years away. So our diameter, 100,000, multiply that by 20, and that's how far Andromeda is. But Andromeda is so big that, and maybe when we go to the planetarium, if we get to go, you'll hear about that in the last time's YouTube video, the possibility of that or not. There is a constellation out there called Andromeda. That's where the galaxy got its name. That was some Greek mythological something or another. I don't know my mythology that well. And one of the stars in that constellation is not a star. It is another galaxy. But it's emitting enough light it almost looks like a star. Okay. And we think it's very similar to the Milky Way. I've read somewhere, maybe in our book or somewhere else, it's thought to be maybe a little bit bigger. All right. how do we classify these galaxies? And Edwin Hubble, if you haven't heard that name enough, you know this is a pretty important character here. He classified them by elliptical, spiral, barred, and irregular. Now, elliptical would be something that's sort of like a circle, but expanded in one axis, okay? That's not what we are. We sort of are like a circle. We are a spiral because it has these bands that spiral down toward the thing. Barred, they just sort of shoot out. Rather than being spirals, they shoot out. I don't know if it's 2 dimensions or 3-dimensional. I've never seen a picture of one. I've seen illustrations, but it's been a 2-dimensional picture, but I don't know if it's 3-dimensional in the bars. And irregular, I mean, they just hang around together. Has anyone ever watched, and they may not do it anymore, Stanford University Marching Band? Anyone know what I'm talking about? You know how most marching bands are just as precise, moving around, and oh, you can just see the figures there. They don't even dress alike, or they did used to. They may have come back into the fold. They used to dress however they wanted to. They're a bunch of engineers, you can't control this. And what they would do, they just run out onto the field and get into the position. And they change, they just run to the next position. It was just like a bunch of ants, and then suddenly they form into a new thing. That, I think, is what the irregular. They just no organization, obvious organization to it, but they're held together by some sort of central black hole or a collection of black holes. And this is actually a picture of Andromeda, taken from the Hubble Space Telescope. And you see here is that galactic nucleus, and then you can kind of make out the spirals going around. And then there's also other things around. Now, you can't tell if these are part of the galactic clusters within this, or if there's something further out. Okay, that could be another galaxy somewhere there, but much, much further away. It's hard to tell from there because it's not got the dimensions around it. But that's probably what we look like if you were living in Andromeda somewhere. Okay. Make sense? Any questions? All right. Oh boy, we talked about the life of the star. What do we think the life of a galaxy is like? Well, our best, or at least most popular current theory is not the TV show, but the same name, the Big Bang Theory. The real big problem with this is, what was there before the Big Bang, okay? A lot is left to be desired. No one can answer that question yet. But the idea is the universe evolved from an explosive beginning. Now that's quite an understatement, okay? If all the universe, and we're talking about billions and billions of galaxies, each galaxy made up of billions and billions of stars, and they're so far apart and all like this, how could all that have been one little pinpoint of mass? I don't know. Maybe it's not a little pinpoint, a huge pinpoint, but still. Evolved from an explosive beginning. Now, what's supporting evidence? The words that follow this, I can't make it clear for you to understand because I'm not sure I understand it myself. First is what they call microwave background radiation. Now, microwaves, even though it sounds like a short wavelength, they're really pretty long wavelengths. These are low energy waves that along about radio wave type, or maybe a little bit shorter than that, background radiation that they think they're hearing from the farthest away. Remember, radiation travels at the speed of light. So the longer away that we can look, we're looking backwards into time, basically. Okay, that's a hard thing to wrap my mind around. Maybe you can understand it well. And some of the stuff they're looking at from way, way back that gives them some supporting evidence that this seems to be how it started. Another thing is, and this is something Hubble, I think, discovered, that the universe is still expanding. Okay? Now that's a little hard to believe, but I can sort of picture that. It's still expanding, but on a pretty big scale. Okay? Now, I think I'll interject this. Here's something that's even harder for me to understand. It's not just gradually growing bigger. This thing right here, will the expansion last forever, or will it reverse itself and crunch together again? That sounds like a good theory. It sounds like something maybe I could wrap my head around. Until I've read, I think it's in your book somewhere, I can't remember where I read it, that we're expanding at an accelerating rate. So it's not just that we're getting further apart, but gradually doing it, we're getting further apart at a faster and faster rate. Now here's the part that makes that hard to conceive. From the first half of the book, the physics part, the only way you have acceleration if there's a net force behind it. There's something that's still pushing us outward at an increasing acceleration. What could that be? Black holes are sucking things in. What is pushing the galaxy out? I don't know. I cannot fathom what that could be. So large-scale expansion, that's even bigger than this word sounds like. Relative abundances of the elements, meaning that even in those rare elements, there's still quite a few of them. So there have been some pretty major bang at the beginning, okay? Because you can't account for how much of this rare stuff is there. That's not just from supernovas. That's not enough to do it. There's enough there that even of the biggest elements, there's enough there that we can isolate uranium. Now, uranium is a long way from iron, and iron is the last thing that happens in a reproducible type of way. So there had to have been a really big bang to make all those heavier elements. Well, this is another thing that sort of is like this. It's called diffuse cosmic background radiation. So it's sort of like this background radiation. And the COBE, I can't remember what that stands for. It's in your text, I think. Spacecraft has been collecting this for quite a while. So where do we end? I don't really care, because I'm not going to be here to know. But is it going to keep expanding forever? Right now, there's no reason to think it won't, because it's actually accelerating its expansion. Or will ultimately it quit accelerating, sort of hang around for a bit, and then start accelerating in again. Okay? We don't know. We have no clue. I mean, there may be clues out there, but nothing too big. Now, one of the guys, can't remember which one, had this idea. What if you were making raisin bread, and you got your dough and mixed the raisins really all over within, and then you put it in the oven and started it rising. All the raisins get further and further apart. That was one of the early ideas of what's happening here. Okay? Large-scale expansion. The problem is they're accelerating and getting further apart. Raisin bread, they may start fast, but then they start slowing down. These are getting faster as they accelerate. Okay? You can read more here, and that, by the way, is Hubble's law. Okay. Y'all are probably way too young for this. You've probably seen some of the movies. Were any of you Star Trek fans? Not Star Wars. I know most of you are probably Star Wars fans. The old original Star Trek fans. Good for you, okay? There were some things in it I'm sure were based on science. Gene Roddenberry was a pretty good interpreter of science. But What did they say in the beginning of that? Didn't they say galaxies far, far away? Or did they just say stars far, far? I can't remember now. I used to know that thing by heart. It's been too long. And the old gray cells ain't what they used to be. But remember, Kirk would have the Ruhu, is that how you said her name, call Starfleet Command and expect an answer within a day or two. Here are some numbers. Mars, if we were talking, using radio waves, not sound waves, radio waves to Mars, that's the speed of light. If I said something to you, 4.3 minutes, the two-way communication for you to get back to me, 4.3 minutes. That's Mars, our second closest planetary neighbor. Jupiter, on the other side of the asteroid belt, 35 minutes to get an answer. Okay? That wouldn't fit in an hour TV show, right? Okay, no, I'm just making that. Okay. Saturn, the beautiful ring planet out there, 1.2 hours to get an answer. Uranus, the next planet out, 2.6 hours to get an answer. Neptune, 4 hours to get an answer. Pluto, on average, about 5.3 hours to get an answer. Just to call across the Milky Way, 100,000 years. I think it's 200,000 years to get it. No, to get an answer. Yes, it would be 100,000 years to get the message across there. So, no, you couldn't have even got to the nearest star and communicated with Starfleet Command within years. Okay, within years. Okay, so not, yeah. To Andromeda, 2 million years. And I think that's a one-way, not two-way, one-way communication. 2 million years to get the message there and another 2 million back. Okay. Then, top of page 369. I mentioned what's on 371, dark matter, and I didn't even begin to skim that surface, but here we have dark energy. And that seems like almost a contradiction. I'll let you read this. It's really almost mind-boggling. The energy that's out there, we can detect because of what it's doing to matter, but we don't know why. We don't know the source of the energy. We don't know how it came from. That's why it's called dark. Okay? Now, they have an equation here, but this is based on stuff that was covered in the first half of the book, so you're not going to be responsible for this. And there's a couple of examples. They're worth a read just to get an idea of what they're talking about, but don't get too bound up with them. I'm not going to give you any of those kind of things to do on the test. It's mostly qualitative stuff, not quantitative. Okay. Page 370 talks more about dark energy and dark matter in the text, and then 371 is almost an entire page on dark matter as a closer look. And I think we're really close to, okay. I don't see the equivalent figure for this in your text. This is from an earlier edition. They think there was a Big Bang, and then you sent all these galaxies, they show all the spiral galaxies here, out there, and they're getting further and further apart as they move outward. Now, what we think we're measuring with some of those things is we're measuring energy from way back here, you know, and it gets to be a bit crazy, it seems like, but, and this is two-dimensional, this is in 3 dimensions, you know, it's happening. not just in the plane of the board, but above the board, below the board, out there, wherever. Pretty incredible, our universe. And that ends the slideshow. Now, let me tell you, for those who have purchased books and those who will be purchasing books, how much were they in the bookstore, by the way? I hope not too much.
86.
About 86 bucks? Okay. Still pretty high, but not nearly as much as this would have been. I'm sure that would have been probably more than 200. So you got almost half the book for way less than half the price. Any of you get used ones? Okay. Seems like some people would have sold them back, but whatever. At the end of the chapter, you'll see there's a summary. Don't rely on the summary, please. Nothing replaces reading the text. Now, the best thing to do is read it before I talk about it. And then, even while you're reading, and I know because I was there, I told you this before. First time I read the text, and this was several editions ago, I was doing more of this than understanding. And sometimes it felt like I was just calling words. But then when I read it the second time, which would be equivalent to me talking about it, your synapses in your brain starts tying some of the things together. So it's a good idea to read it first. If not, read it while I'm talking about it, but read it at some time. But once you've read it and things seem to be making sense, then the summary is a good thing to look at. That's just a few paragraphs. The text is pages and pages and pages. It summarizes it. Now, some of the words here are italicized, and they're pretty important to pay attention to. They list a summary of equations. Don't worry about those. Those deal with math levels sometimes higher than what you're required to have. But then there's the key terms. The key terms pretty much compare to some of those that were italicized in the text. Now, the thing is, the key terms are in alphabetical order, but they do give the page number where the term was either first introduced or explained, so you can sort of piece those together. But the very best thing they have in my mind at the end of the chapter is applying the concepts. This chapter has 50 multiple choice questions. Applying the concepts. A great thing to use as a study guide. And remember, the test is next Tuesday on this chapter. Okay, chapter 14. I can almost guarantee you none of these questions will be on the test. But questions on the test that cover the same topics, maybe just put a different way from this, some of these will show up there. Not as the same questions, but as a variation on the same thing. So this is a great thing to look at. Now, is it just questions with multiple choice answers? Well, it's that, but at the end, they give the answers. Which of these four, these are always four choices, which of the four choices are right? So it's a great thing to go through, answer yourself, check your answers here, go back in the book, figure out why you may have missed it. If you cannot figure out why your answer is wrong and this one's right, that's a good thing to bring to class. Remember at the first of class today, I said, are there any questions? I'm going to try to ask that every time. If you find something here, you don't know why that's an answer to that multiple choice question, bring it to class and we'll discuss it. Okay? And it will be helpful for everybody. It might let me know there's some wrong answers here, or not, that there really are. Now, the next thing they have here is questions for thought. Oh, and by the way, 50 is about average for most of these chapters. Maybe a few more than average, but right around the average. The questions for thought, there's 21 of those. That's a bit more than average, too, if at least my memory of what's average. Then there's for further analysis. Now, I can't tell a lot of difference between those two, but there's only 5 of those. That may be average or a little bit less than average. Okay? Now, there are also parallel exercises. Those are mostly solving problems using some of those formulas. Don't get too tied up with that. You won't have any of those on the test. Okay? However, looking at that, Now, I asked them when they did these customized texts to put the answers in the back, and the ones I've seen from students who gave them to me, I can't detect they put the answers there. If you find those answers, let me know. But it's not really important because you're not going to be tested on that. But they do mention several stars. I see Vega, I see Sirius, I saw Arcturus. There's a lot of things here that, and Betelgeuse, I see Betelgeuse there. There's a lot of things here that you can sort of relate to, but don't get too bogged down with it. But they may give you good ideas for paper topics. All right. Any questions on 14? All right. What's that?
I have a question about that.
I usually shoot for around 20, but most of the time I can't get 20 on 2 pieces of paper, so I cut them back. So I think on the neighborhood of 20. May have 1 or 2 tests that exceed 20. Most of them will be fewer than 20. Okay. And like I said, there's 50 here, multiple choice questions. So not going to cover everything here, but if you know that, you have a really good chance of doing well on the test. Okay. Any other questions? Good questions, by the way. All right, let me shut this down, and we'll move on to chapter 15. Now it's 2:53. That means we've been going at it from 1:15 about an hour and a half. Is that about right? Hour and 45 minutes. This a good time for a break, or want to go a little bit longer, get at least closer to halfway? Half time to take a break. Anyone have a preference? Take a break? Okay. Let me put this on let me get this loaded up, and I'll put it on pause, and we will take a quick break and come back soon as you can. Okay, the question was, what's the name of the book? Physical Science by Bill W. Tillery, Tillery. It's the 11th edition, though if you find an earlier edition, nothing has changed to speak of. They just get more money if they come up with new editions. I've got the ISBN number. If you want to take a picture of that, you can get that off of here too. We haven't covered anything new. Okay, we've been waiting. Okay. Any other questions, by the way? All right. Oh, let me do this from current slide. All right, chapter 15 is, we started big, the universe. Now we get down to our solar system, okay? And toward the end of that, remember when we were just talking about how long it would take to send messages across our solar system? That's what we're getting to now, this small-scale stuff, okay? We'll talk about something about this later. There's no reason going into it now. The core concept here, which you find on page 378, now these are the big number of pages, not the little number of pages that would be of your individual book. The solar system is composed of the sun. That's what Sol means, sun. S-O-L for solar system, sun. And the orbiting planets. Okay? How many planets do we have? Anybody? 8, exactly. Okay? And dwarf planets, we'll name at least 5 of those. There may be some more. Okay? And then what we call small solar system bodies. That will include the moons that are around the planets. That includes the asteroid belt that's between Mars and Jupiter. It includes the comets. It includes meteors, meteorites, meteoroids, just about everything else. Small solar system bodies. Okay. Let's start with how we name these things anyway. There is a body called the International Astronomical Union. The IAU is the governing body. Now notice international. It's not U.S., it's not European, it's not Soviet, it's international astronomical unit. I would say this is probably one of the prime examples of how we really could live together on the planet as scientists, astronomers anyway, have done this and it's worked. Okay? Why can't anybody else? Okay? Probably some people can. International Astronomical Union, governing authority over naming of the celestial bodies. Okay? And sure, early on, I bet you it was dominated European type names because they were the ones that were recorded, but there are all sorts of names out there now. And the IAU also defines what makes a planet a planet. What makes a dwarf planet a dwarf planet. What makes the smaller solar system bodies and which way we classify them. Okay? And in 2003, that was probably, most of you were born by then, weren't you? Okay, good. Okay, but you were pretty small, young. Long time ago. Okay. In 2003, Pluto was redefined as a dwarf planet rather than being a planet, which we had always considered it before. And we'll talk about several reasons for that, but not to get into any super technical reasons. Okay, we'll just give sort of some of the big ones. Now, here is, okay, please, if someone comes in and you weren't here before, tell me because I may miss it, but I think all of you have been. To be a classical planet, an object must be, and here's several criteria, orbiting the sun. Okay? Well, of course, that's why everything orbits the sun. But the orbit needs to be nearly spherical. Okay? That's one place Pluto falls out. There are some times that Pluto's orbit is inside that of Neptune, but most of the time it's outside that of Neptune. So it's a highly elliptical orbit, not nearly circular. So that was one. Okay? Large enough to clear all matter from its orbital zone. In other words, large enough to its gravitational field is going to pull stuff in that gets in its way and it's going to be, cause it to become meteorite. Okay. Now, a dwarf planet is defined as the object that is orbiting the sun, sufficiently massive to gravitationally reshape itself into a sphere, and Pluto had done that, but has not cleared matter from its orbital zone, and is not a satellite. Ooh, why did they have to put that in there? There are some moons, I think probably one or two of Jupiter's, at least one of Saturn, that are actually bigger than Mercury. Okay, so, but those can't be planets because they are satellites of another object. So that's why that was put. And they can't even be a dwarf planet. Those moons are probably at least four moons of Jupiter that are bigger than most dwarf planets. They're probably all dwarf planets. Okay, so they can't be a satellite. Okay. They are spherical and everything else. All other objects orbiting the sun are referred to collectively as small solar system bodies. Okay? Now, here's a few of the sort of classifications and definitions that you might need to know. Okay. The solar system is made up, as we just said, the sun at the center, 8 planets that we know about. Has anyone been reading or keeping up with scientific investigations of our solar system? There are a lot of scientists, maybe not a majority, but a lot of scientists who think there's enough evidence to support the fact there's some 9th planet out there. They're not talking about Pluto. They're talking about one that would be equivalent to, on average, Neptune and Uranus. Big old planets. because there is enough gravitational disturbance there. But it could be it's so stinking far out there that we can't see it because it's reflection from the, planets reflect from the sun. It's so far from the sun we haven't been able to detect it by the light that reflects it. Of course, it could be it's on the opposite side of the sun and so far away that it hasn't come close enough for it to detect in the thousands of years since we've been looking out there. And that could be because they're way, way out there. But right now we know of 8. There are approximately 100 moons. I think that's a bit on the low side because if I'm not mistaken, Jupiter has between 50 and 70 moons itself, and Saturn has quite a few, and the other big planets have quite a few moons. There are literally thousands of asteroids, millions of icy bodies, think comets, icy bodies, and then comets, okay? The astronomical unit, now this isn't the astronomical union, astronomical unit is the average Earth to Sun distance. It's about 1.5 times 10 to the 8th kilometers, which is about 93 million miles, okay? 93 million would be 9.3 times 10 to the 7th, and this is 1.5 times 10 to the 8th. So the numbers are pretty close to each other, but that's in kilometers, this is in miles. Okay. Now, we only use astronomical units when we're talking about the solar system. They are way too short, too small to talk about anything beyond the solar system. And even they're pretty small compared to many things in the solar system. But that's what one astronomical unit is, the average Earth-Sun distance. Now, why do we say average? Because we don't have a perfectly circular orbit. We have a slightly elliptical orbit. There's sometimes we're closer to the sun and sometimes further away. So that's why they say average Earth-Sun distance. Now, how do we classify those 8 planets? Well, size is 1, density is 1, and atmosphere is 1. Okay? Now, they say that and then split them up into 2 classifications that sound like they have nothing to do with either one of those, but they really do. The 4 closest planets to the sun, Mercury, Venus, Earth, and Mars, are called terrestrial planets. Now, where that comes from, they're rocky. Okay? They are mostly rocky materials. Now, we're talking on the surface. The metallic nickel and iron is the predominant element in all those 4. Metallic, copper, and iron. Wait a minute, Earth isn't mostly nickel and iron. Earth's not mostly nickel and iron, or is it? Seems like we got a lot of rock, not much iron. That's on the surface, folks. Only on the surface. Down deep, mostly nickel and iron. We've never been down there, but we see it erupting every now and then. Okay. Then the 4 outer planets, Jupiter, Saturn, Uranus, and Neptune, are called the giant planets. They're sometimes called gas giants. That's because their surfaces are not solid, not rocky materials. Their surface is it's just gas. Okay? If you go down deep enough, you may hit other material, but it's just a gas. Okay? Mostly hydrogen, helium, and strangely methane. Okay? Now, hydrogen and helium I was expecting. Okay? Why? That's what the sun is, right? Mostly hydrogen and helium. So when it was going through its dynamical equilibrium, and forming from protostar to star, probably having explosions everywhere, stuff got spewed out. Not at all surprising that hydrogen and helium got spewed out. Methane? What is methane? Anyone know? Say again? Yeah, okay, right. Okay, got it. Now I understand what you were saying. You don't need the pipe. No, I'm kidding. It's a gas made up of carbon with 4 oxygens, CH4. Okay? You can find that. Okay? Yeah, you're right. Okay. With some hydrogen sulfide in it, what you were saying. Okay? Look, this is methane. Okay? Now, to me, methane, carbon, see, before I got into this at all, I would have told you methane is produced by organic matter because it's got carbon in it. It's what Ian was talking about. But guess what? There's no cows on those outer 4 planets. Okay, I can guarantee you that. That's not where the methane's coming from. That came from carbon with 4 hydrogens. Carbon must have been from the fusion of helium. Okay? So sometime way before, there must have been another star out there that produced this. Now, the 4 inner planets, I'll just tell you this now, there's some hydrogen, some helium, and certainly some methane in their atmosphere, but it's very, very minor. The 4 outer ones, predominant. So the idea here, and we'll get into this later, is that when the sun was doing all this explosion, the hydrogen and helium being very light, and methane really light, got blown way out there. Not much left of the atmospheres of the 4 inner planets. Okay. And then there's Pluto, no longer considered a planet, but now considered a dwarf planet. Now, let me tell you a couple more reasons. We already said its orbit is way too elliptical. Okay? Another is, if you were to look at Pluto way out there, most of the time beyond Neptune, if you look at it, it's more like a rocket. It's more terrestrial than it is. So it doesn't fit with the others, at all. Okay. Now, I do want to read you something from the text. I want you to read it too, but I want to, okay, wait, let me back off. Dwarf planets, okay? This probably was from this slide here. Dwarf planets. Let me read you the name of the at least 5 dwarf planets that they've named and identified. Pluto being one, Eris, E-R-I-S, Ceres, C-E-R-E-S, and this, I don't even know if I'm pronouncing this right, but I think it is, Makemake, M-A-K-E-M-A-K-E. It's like make, but I think it's pronounced Makemake. And Haumea, H-A-U-M-E-A. I'm not standing by the pronunciations at all, but those are the 5 dwarf planets that we know about. Now, what's that?
What page is that?
That's on page 379. Okay? Just so you will have heard those names at least once. Okay? Now, here is a statement, and there's a reason I'm reading this statement from the book. Because, let's see, I think I'll go back to this. Where was the astronomical unit? Oh, yeah, there it is. Okay. I want you to catch this sentence. The sun, remember that's one of the objects in our solar system. The sun has 700 times the mass of all the planets, all the moons, all the minor members of the solar system combined together. Okay? So this sun in the center of this is more than 700 times the mass of everything else. Everything else. More than 700 times. So, okay. Now the reason is, later there's going to be a slide that says something, but they don't quite have it phrased right. And I want to make sure you understood that. The sun is more than 700 times everything else put together. Okay, that's from page 379. All right. Now, the order of the planets. They never look like this. Ever. Ever. Okay? There's so many things wrong with this picture. Now, relative sizes, not bad. Not bad at all. Mercury is by far the smallest planet. Now, if you included Pluto, which they do for some reason, this is not a planet, it's a dwarf planet, it's actually smaller than Mercury, I think. I'm pretty sure. Okay? But Mercury's the smallest. Now, the relative sizes you see here are, even the moons are pretty good. And you can't tell for sure because they're gray dots and it's hard to see here. But there are several moons, at least one around Saturn and several around, at least one around Jupiter that are actually bigger than Mercury and way bigger than Pluto and any of the other dwarf planets. Okay. Now, so the relative sizes aren't bad. Two things that are just totally wacko about this picture is they never, ever, ever, ever will line up like this. Okay, so don't ever expect them to. This is just so you can see them in a group. The second thing that's probably, okay, let me back off about relative size. The planets, their moons and that kind of stuff, relative sizes are about right. Sun in there? Sun is 700 times more massive than all these things put together, and size-wise is even bigger than that. Okay, so don't even think that Jupiter is that close to the size of the Sun. It's not, nowhere close. So the Sun's size is completely out of proportion. But the other thing that is absolutely out of proportion is the distances. Okay? And we'll talk about this a little bit later. The relative placement is right. Mercury, Venus, Earth, Mars, Jupiter, Saturn, Uranus, and Neptune. Okay? That order is correct. The distance is nowhere close. The inner four sort of right, but the outer four is almost that every time you go to another planet, and we'll talk about this later, you get almost between 50% and twice the distance from the previous one. So these are staying way too close together. In reality, they're way, way out there. These would be so tight you wouldn't even distinguish them, and these would be so far apart you couldn't fit them on the page. So the relative distances are totally wrong here. And the fact that they would line up like that is fictitious. Okay. Now, they're going to start the process of going through each planet separately. I wish they had shown this table first, table 15.1 on page 381. Okay? And I think I'm going to go back to this slide. No. Yeah, this slide. Where it says here, planet classifications on size, density, and atmosphere. So let me summarize at least some of that from this table. If you got your books, it's really a good table to look at and study. And some of what they're going to talk about here will come right out of the table. But let me point this out to you. The average distance from the Sun, so let me go to this fictitious table picture here. Okay? If this is Sun, center of Sun to Earth, okay? At least I think this is center of Sun and not the surface, the edge of the sun. They don't specify that here. About a third of the way from the sun to Earth is Mercury. Okay? About 3/4 of the way from sun to Earth is Venus. That looks pretty reasonable. Okay? Earth is 1 astronomical unit from the sun. Then to go Earth to sun, you would do half that distance further to get to Mars. They have Mars a little close, but it's 1.5 times what Earth is. So half the distance here, and you get to Mars. But then, what it is from Earth to sun, more than 5 times that, there would be where Jupiter was. Not here. Nowhere close to there. Okay? Then Saturn is almost twice as far as Jupiter. So if Jupiter was here, Saturn would be somewhere twice as far as Jupiter. And then Uranus, twice as far as Saturn. Okay? So you're almost doubling what the previous planet was to the next one. Now Neptune doesn't quite fit that. It's 30 astronomical units. Not twice what, but it's pretty close to it. So those gas giants, they'll go way out there. Way, way out there. That's what I meant about the scale here not being close. Okay? Now the inclination to ecliptic. Ooh, what in the world does that mean? Anyone know what the ecliptic means? Anyone know what an eclipse is? Okay, say a little louder. Yeah, with what? Earth, okay, excellent. There's 2 types of eclipses that we usually think of. You were describing a lunar eclipse. There's also a solar eclipse. Okay. Now the lunar eclipse, and actually you're describing solar too. Okay. The lunar eclipse is when the moon passes in the shadow. In other words, it's perfectly aligned between sun, earth, and moon, and the moon passes in that shadow. See, normally that would be a full moon, but if it passes in the shadow of the earth, then it goes from being full moon to not looking like a moon at all, and then coming back out again. A solar eclipse is when the moon is over here, and it's perfectly in line with the sun. That happens in daytime, okay? Usually sort of around noonish, but not always, so that would be a solar eclipse. Okay, so an ecliptic is when you're in the plane of the sun and the earth. Okay? That's your ecliptic. It's the plane form of the earth going around the sun. That forms a plane. Okay? That's the ecliptic. So, what they're talking about here are the angles, inclination to the ecliptic. Because Mercury is so close to the sun, just over a third of the distance from Earth to sun is, you find Mercury. It's not far off, but because it's so close, the angle is up to 7 degrees. It doesn't sound like a lot, but that's the biggest. If we included Pluto, which is the furthest out planet, it's something like 15. That doesn't make sense. That's way, way out of the ecliptic. There's another reason Pluto isn't classified a planet anymore. Its orbit is way outside the ecliptic. Okay? Then Venus, which is next closest to the sun, 3.4 degrees. Earth, 3.4 degrees, about half of the angle that Mercury makes, but it's twice as far from the sun, so it's probably not too far off the same plane as, or its plane isn't much further off than Mercury's is, just a bigger angle because Mercury's closer. Earth is 0 degrees, and then you notice Mars is only 1.9 degrees off, Jupiter 1.3. You don't have to know these numbers, but just get an idea. They're very small numbers. Saturn 2.5 degrees, Uranus 0.8 degrees, and Neptune 1.8 degrees. All of them very close to the plane. Okay, very close. Furthest off is Mercury, and it's only because it's so close. Pluto's somewhere out there, way off, big degree, but so far off, way off from the ecliptic. Okay. Now, what's that?
What was the Uranus number?
0.8.
0.8, okay.
Okay, degrees. Okay. Remember, a degree is a pretty small angle to begin with. 360 of them makes one circle. So it's a pretty small degree. Now, the orbital period. Now, we're going to base everything in Earth years. And if you think about it, of course, the planets close to the sun are probably going to go around faster. I mean, it'll take less time to go around because they don't have to go as far. And the ones further out are going to be greater. So let's see what they are. Mercury's about a quarter of a year, 0.24. Venus, 5/8 approximately, 0.62. Of course, Earth is 1 year, okay. Mars, 1.88 years, so almost 2 years for Mars to go around the sun. Jupiter, 11, almost 12, 11.86 years to go around the sun, Earth years. Saturn, 29, almost 30. Uranus, 84.101. Neptune, 165 approximately. Way long to get around the sun. So if there is another planet out there, and it's probably going to take around 350 years to go around the sun. And if we're traveling here and it's here, yeah, it's easy to imagine we haven't yet gotten close enough to see it. Or if we've seen it, it was just such a blur that we didn't know what we were looking at. All right, rotational period. Now you would think, okay, orbital period is to go around the sun. Rotational period is to spin. Now, there's no real reason to think that the different planets would have different rates of spins. Okay, not too much. But there's no reason to think they'd have to have the same. So these, you would think, would be a little closer, and they kind of are. Mercury, though, spins once every 59 days. We're 24 hours. They're 59 days. So it's not spinning very fast at all. Venus? Uh-oh. Venus is spinning. To spin once takes 243 days. But in the table, you notice something really bizarre. What do you notice? A negative sign. That means it's spinning backwards. All the others, except Uranus, are spinning in the same direction. And the sun's spinning in the same direction. There, Venus and Uranus are spinning backwards. Now, Uranus is really strange, too. Say again? Yeah, in other words, if you're on Venus, which I'm glad you're not, and you don't want to be on Venus, but if you were on Venus, the sun would rise in the west and set in the east, because it's spinning the opposite direction. You don't want to live there, okay? You'd never see it rise and set. If you saw it rise, you wouldn't see it set. Okay, never mind. 343 days is one spin. Now, I'm going to jump a little bit ahead. I can't remember if this is in the book or not, but there is a big thought that Venus must have had a really major collision with something really big. Okay? And that collision basically knocked it so hard it reversed its thing. Because it's moving awfully slowly, but in the wrong direction. Okay? And all the others except Uranus. Now, Uranus is strange in itself. We'll get to that when we get there. Okay? Earth, about 24 hours, actually 23 hours, 56 minutes, and 4 seconds. Okay? We'll say it 24 hours. Mars, 24 hours, 37 minutes, and 23 seconds. You can't get much closer than that. Okay? Jupiter, though, really is spinning fast for a big planet like that. 9 hours, 50 minutes, 30 seconds. You don't need to know all this. Saturn, 10 hours. Uranus, they have a minus there, 17 hours. And Neptune, 16 hours. So you see, most of the others, except for the two closest ones, are going in numbers of hours. Mercury, 59 days, and Venus, 243 days, spinning backwards. Okay, now Uranus. Here's one of the reasons for its minus sign, and we don't know why. Maybe it had a big collision too. Its axis is almost horizontal, not vertical. Okay, and it seems to be spinning backwards too. But which pole are you looking at? I mean, so it must have gotten whacked too. We don't know that. We don't know enough about Uranus to tell. It's going about the right speed, but now here's things to note there. Okay, if you combine those two, it takes a quarter of a Earth year for Mercury to go around the Sun, and it takes a sixth of an Earth year for it to spin once. So its days and its years are pretty close to each other. But then look at Venus. Its orbital period is just over half that of the Earth, but its day is more than half a year. So actually it spins more rapidly. Am I saying this right? No. It goes around the Sun. Its year is longer than its day. Is a weird way to look at it, but it is. Its year, it goes around the Sun faster than it spins on its axis. And it spins backwards at that. Bizarre. Okay. That's all I'll say about those. Masses. Mercury is very small mass, 0.05 Earth's mass. Venus is closest to Earth, that's 0.82 Earth masses. Earth, of course, is 1 Earth mass. Mars, to me, surprisingly, is very low mass. Okay, 0.11, about twice what Mercury is. Okay, Jupiter, they call them giants for a reason. 318 times the mass of the Earth. Saturn, 95 times the mass of the Earth. Uranus, 15 times the mass, and Neptune, a little more than 17 times the mass. So those gas giants are indeed giants. Okay? Now, equatorial dimensions will refer to an Earth radius as 1. Mercury is about a third, a little more than a third, the radius of the Earth. Venus is almost exactly 0.95 the radius of the Earth, and of course the Earth is 1. Mars is about half the radius, a little bit more than half the radius of the Earth. Jupiter, 11 times the radius of the Earth. They don't call it a giant for nothing. Saturn, 9 times the radius of the Earth, and both Uranus and Neptune about 4. They are almost the same size. Okay? Uranus being a little bit bigger in volume, but Neptune a little bit bigger in mass. So they don't quite have the same density. And that leads to density. Mercury, and these are not relative to Earth, just numbers, 5.43. Venus, 5.25. So actually, Mercury is a little denser than Venus. Earth, 5.52, which means so far it's the most dense. Not by much, but a little bit. Those inner three, really very close to each other, with Earth being the densest. Mars, terrestrial, but only 3.95, almost 4. So not quite as dense as the inner three. But you get to the gas giants, look at their densities. 1.33, they're made up of gases, not solid, not rocky materials. Okay? Saturn, 0.69? What does that mean? It's less dense than water. So if you had a big enough tub and you put Saturn in, it would float. None of the others would. Saturn would. By far the least dense of the planets. We don't have that big a tub, by the way. Okay? Uranus, 1.29, and Neptune, 1.64. So your gas giants, the densities are down in the ones or less, Saturn being less. The terrestrials, 4 to 5.5, with Earth being the densest. We finally came out ahead on something, right? Okay. Atmospheres, remember? Okay. Back to here. Classified by atmospheres. Here, Mercury stands out. Absolutely, or basically no atmosphere. No measurable atmosphere at all. Okay? Now, you can probably easily imagine why. If when the sun was blowing up and doing all the things like that, probably blew the atmosphere right off the sun, off of Mercury. Doesn't have a bit. But then, on the other hand, Venus is probably the densest, well, it's hard to say, of the terrestrial planets is the densest atmosphere. And it's mostly CO2, carbon dioxide. Now, before I read this text, I would have sworn to you carbon dioxide is manufactured from organic matter. Venus is not manufactured by organic matter. It's naturally occurring CO2. Now, what do we know about CO2? You hear it talked about in science terms today a lot. What is carbon dioxide classified as? You've not heard anyone talk about it? Someone chose as their paper topic global warming. And what is one of the contributors, they think, to global warming? Carbon dioxide. Now, our atmosphere is very low percentage carbon dioxide, but that percentage has gone up since the Industrial Revolution began many times what it had been for millennia before that. So that's what we think is contributing to global warming. So guess what that will make Venus the hottest planet. Even though Mercury is closer to the sun, on average, Venus is the hottest planet because that really dense atmosphere it has, mostly carbon dioxide, holds the heat like crazy. They call it a greenhouse gas. Greenhouse meaning trapping the heat. Okay? Earth, unique in its atmosphere. Anyone know what the predominant element in our atmosphere is? Or compound? Nitrogen, then oxygen. Close to 80% nitrogen, not quite, 78, something like that. Oxygen, close to 20%, not quite, maybe 18 or 19%. All the other gases added together, just a few percent. Okay? Mostly nitrogen, next most oxygen, and not and very little else. And then jump across Earth, and what do you find on Mars? Carbon dioxide again. What? Why would that be? Does anyone know why oxygen is so prevalent in our atmosphere? This is sort of a theory. What you say? Say again? I think, here, sick for you. You're thinking like I do. Okay? We have green planets. Oxygen is a very reactive gas. So oxygen doesn't exist as O2 very many places except that those green plants are pulling in carbon dioxide and sending out oxygen. If we didn't have those green plants, guess what? I don't think oxygen would be our number 2 in our atmosphere. It might wind up being, I think it'd still be nitrogen as number 1, but carbon dioxide would probably be number 2. Because all that oxygen. But green plants are giving us life. Without them, we don't exist. because we wouldn't have oxygen to breathe. And we got to have oxygen to breathe to oxidize our food, okay? And to do everything that we do, we've got to have it. Thank you, green plants. And does anyone know what's going on right now in Brazil? The Amazon rainforest, huge portions of it are on fire. Guess where the biggest source of oxygen-producing green plants are? Well, in our rainforest. And that's one of the biggest. Folks, things could be getting tight. And I guess the president of Brazil is one of these deniers. It has nothing to do with climate change. Yeah, right. Not only has it got something to do with it, it's now contributing to it big time. And the sad news is they've been doing it on purpose for a while, trying to produce more farmland out of those rainforests, and they can't sell all the timber, so they just burn it. So, sad. Different topic. Okay. Okay. Moving on out, past the asteroid belt. Remember what they said the predominant gases of the gas giants? Hydrogen, helium, and methane. And there you see Jupiter, hydrogen, helium. Saturn, hydrogen, helium. Uranus, hydrogen, helium, and methane. Neptune, hydrogen, helium, and methane. Okay, so yeah, for sure. Now, the next is just sort of a duh kind of thing. Solar energy received, the ones closest, Mercury, receives the most solar energy per unit, per square centimeter, and they just drop off like crazy from there on out. So that's nothing all that new. Okay. Boy, that was a lot, wasn't it? How are we doing on time? Oh! Did you do it? Did you let me sneak past 3:40? Oh, okay. All right. We will start next time with Mercury, okay? We are pausing right now, and we'll get ready for our lab. So, do y'all want to take a little break, or has it been too recent since the last break? Okay. I'm going to...
So what do we decide? We're going to try to go part way and then take a break?
Yeah, I couldn't hear that.
What did they decide? Are we going to go a little while and then take a break?
We could. Actually, once we start the lab, people will be moving around some, so I don't think it'll be as necessary. So if you need a bladder break or food break or water break or something like this wouldn't be a bad time to take it. You want to take it or not? Okay. That'll give me a little time to set up, too. So I'm going to pause. Oh, should have done this before I started again. Need to call roll again. Y'all were supposed to remind me, weren't you? Oh, call roll. Thank you. Thank you so much. Okay. All right. Luis is still here. Lexi is still here. Zarit is still here. Brianna is... Did we lose Brianna? I think we did. CJ, still here. Got it. Ethan, still here. Got it. Amanda's still here. Jordan is still here, right? Yep, thought you were. Jonah and Patrick are kind of here. Okay. Maurice is still here. Cameron. Yep, got it. Derek. Yeah, got it. Thank you. Tegan is still here. And Chris Levins hasn't made it yet. Okay. Latricia. Got it. Thank you. I saw you back there. Heaven's still here. Ian is kind of here. Okay. Okay. All right. Edward is here, right? Yeah. Okay. Got it. And Jamar we haven't seen yet, have we? Let's see. Yes. All right. Ken? Did we lose Ken? Looks like we may have. Terica or Tarika, how do you pronounce it? Oh, we lost her. Oh, she wasn't here today. So I don't know how to pronounce it. Diamond, got it. Tamaya. I think she's coming back because her stuff's here, but we'll hang on to it and see. Ruben is still here, and Ryan is still here. And Tamaya, right? Okay. All right. Anyone whose name I didn't call a second time? All right. Now, close this, I think. Did everyone get a copy of the lab? Okay, and there was a question, can you write on this? Yes, this is what you're turning in for your 25 points. Okay? So let's talk a little bit about what's front. Now, all that time, I'm sure you were reading the first couple pages. Be sure you read this. Let me go over some of the high points here. Okay? Let's again refer to what we mean by a meridian. If we imagine a line extending from the north point, due north, this is approximately right, I'm guessing, on the horizon, passing directly overhead, okay, and then continuing to the south point on the horizon, that is your local meridian, okay? Wherever you happen to be, that's your local meridian. Now, when the sun crosses that meridian, and it does it once a day, crosses that meridian, we say that it is said to transit the meridian. And by the way, that will be the highest point the sun will ever be on that day. Before it crosses your meridian, it's below it. When it crosses, that's the peak, and when it after that, it's on its way down. Okay? That will be the highest point. Same thing true of every star or anything else where it crosses your meridian, your local meridian, that will be the highest point. Now, we've also mentioned this in the lecture today. Let me give my handy-dandy visual aid, and that is the globe here. Now, I'm having the North Pole pointing close as I can to due north, and let's just say, who wants, well, we won't do due north, we'll pretend due north this way. All right, we'll do it this way. Okay. Who wants to be the sun? Amanda, you look like you're pretty bright, okay? So you'll be the sun. The plane that cuts the earth through the sun, that is the ecliptic. Because anything along there is going to be eclipsing the sun or being eclipsed by the earth's shadow of the sun. So that's what your ecliptic is. So, bold word, who just came in? Okay. Did you get a copy of the lab? Mm-hmm. Okay, good. And let me make sure I've marked you. You were marked? No. I know you're not Brianna. Okay. Is it Ken? Okay, I thought so. And by the way, folks, if you haven't noticed it already, I have a really good memory. It's just short, and sometimes I have trouble with it. So most of the time, I'm remembering more about where you sat than who you are, okay? I'm terrible with names and faces. So if I miss you and confuse you more than 16 times this term, then you can start throwing things at me. Okay, so y'all going to keep count, right? Okay, when it gets over 16, you can start throwing things. I'm hoping that'll be by the end of the mini terms. Never mind. Okay, so anyway, that's the ecliptic. The path, noticing the sun's position among the stars at sunset and sunrise each day, we can plot this path among the stars, and that path turns out to be a circle, which is called the ecliptic. Okay? So, now, the sun creeps from west to east in a nearly uniform rate. Okay? Moving every day a little bit further from west to east. Okay? Now, it takes about 365 days and almost 6 hours to complete a single circuit all the way around, right? Now, that's coming up on page 360, then, the second page here. Part A, celestial pole and the equator. Okay? Now I'm going to try to reproduce a drawing similar to this one here. Okay? This might be in the way. Will it be in people's way if I set it right here? Is that in anyone's way? Okay. Now, just to get a little bit of kind of a perspective or an idea of what's going on, let me get my pen set up here. Okay. I'm going to draw the little globe here. Ooh, that's a pretty ugly globe. Okay. But you get the general idea. Okay. All right. Now, here is our horizon. Because we are standing, this is where we are. There we are, standing right there. Okay. Bit big, but okay. All right. Now, where we happen to live, I'll go get another page here so you'll know I'm telling you the absolute truth. Or at least close to it. Okay? This is an Alabama Atlas and Gazette, and it has in it latitudes and all sorts of things in it. It's a great piece. We'll use it a few times in this course in labs. Okay, we're in Bessemer right now. That puts us pretty close to 33 degrees, 23 minutes, and 45 seconds. That's our latitude. That's how far we are above the equator. So if we're standing right here, here is the center of the Earth, that means the equator is about, does that look like it could be 33 degrees? It looks fairly close. So this is the equator here, and this is 33 degrees, 23 minutes, and 45 seconds above the equator. Okay? Now, this is our celestial sphere. Not a very good sphere either. Kind of a hemisphere. Okay? Now, the celestial, and here we are. And by the way, directly overhead here is our zenith. Directly overhead on the celestial sphere. And that means about that, this would be our celestial equator. Celestial equator. So this would be, in our zenith here, this would be 33 degrees, 23 minutes, and 45 seconds. Now, the book didn't put that in here. It told us that was our alpha. Call alpha. No, that's something else. That's our alpha. So you don't need to carry around these numbers. Just think of that as alpha. Angle alpha. Okay? Now, what we're trying to show, in fact, I've just about blown it here, okay, is this. If I'm holding this here, okay, North Star is up there, okay, we want to know what the altitude of the North Star is, okay? Now, the North Star, I drew our horizon here. This is our northern horizon. This is our southern horizon. So somewhere up here is the North Star. I'm just going to call it Polaris. It's not the thing that swims around in your pool. No, okay. So there's the North Celestial Pole. That's what they call it in the book. North Celestial Pole. And Polaris is there. Okay. Now, what we need to do is to show that our latitude here, alpha, is the same as the elevation, the altitude of Polaris. And in the Navy, okay, when you were in the, do you know if the navigation officer went out and shot stars in the morning and evening?
They stopped doing it.
What's that? Yeah.
We had a staff meeting.
Yeah.
Autographs and stuff, but they didn't do that. It's just that kind of navigation. I think they could, the quartermasters could, but they didn't. You make me feel old, okay? Because when I was in, we still were shooting stars. Okay. And one of the stars we shot, every time we shot, was the North Star. Now remember, it's not a very bright star, but we used the Pointer stars, the Pointer sisters, the Pointer stars to point toward the North Star, and we found it, and we always tried to shoot that. Because guess what? That gave us our latitude. Without question. Wherever we were, that was our latitude. Well, that's what we're trying to show here. Now, why would that be the case? That this angle here would also be this angle here. Well, they go about doing it sort of a strange way. Or it seems a little strange to me. They call this angle over here theta. Now, what can you tell me as a relationship between theta and alpha? 90 degrees. They add to be 90 degrees. Anyone know what we call those two angles that add to be 90 degrees? Complementary angles, okay, but it's spelled with an E, not an I. So they're not telling your hair looks good. It's telling they complete a right angle. Okay. So, that's the case. Now, my figure isn't too precise, obviously. But here's the celestial equator. There is a North Star, or somewhere about there. What can you tell me about the angle between them? It doesn't look like it, so maybe if I drew it a little bit further that way, it might look a little more like it. Probably not. Ooh, didn't erase. Didn't erase. Erase. Get me out of this mess, Percy. Okay. What is the angle between the equator and the North Pole? 90 degrees. So therefore, between the celestial equator and the North Celestial Pole will be 90 degrees. Well, there's alpha part of that. What would this be? That would have to be theta, because alpha and theta are complementary. So this would have to, this would have to be theta, and therefore, between your zenith and the North Pole, north on the horizon, would then have to be another 90 degrees. So if that's theta, this has to be alpha. Right? All right. So that shows, hopefully beyond the shadow of a doubt, that your latitude on Earth is the same as the altitude of the North Star. That's why we shoot it, to find out our latitude. Okay. Now you need to write down enough on this to convince me you understand why that's true. Okay? I was hoping y'all were writing as we did. A few people were. But write down enough on that page to convince me that indeed that was the case. You can read that and you'll find a few helps for that as well. Now, let's take our measurements off of here, because the next question, question 2, is referring, could have left something there, but I didn't. Okay, question 2 on page 361. If the celestial pole makes an angle of 40 degrees over the northern horizon, so this is going to be 40 degrees, north celestial pole, 40 degrees above the northern horizon. You see? Did I do it right? Okay. At what angle over the southern horizon does the equator make? Here's the southern horizon. There's the celestial equator. What angle would that have to be? Say again? 50. You got it. That would be your 50 degrees. Aren't you glad that we didn't use 33, 23, 45? We'll be using that later, but not yet. Okay. Now, suppose you are at Quito, Ecuador. Quito, Ecuador. Does anyone know any idea about Quito, Ecuador? It's what? You got it. The name of the country, Ecuador, guess where that comes from? Equator. You're absolutely right. And Quito, the capital, happens to be sitting almost as smack on the equator as you can get. So we're going to say its latitude is 0. Okay? Now, if you're standing in Quito, Ecuador, let's get what the question is. Suppose you are at Quito, Ecuador, latitude 0. Where is the celestial equator then? Say again?
45.
Not 45. 0 plus what gives you 90? 90 degrees. It's directly overhead. It is directly overhead. Celestial equator, east to west, directly overhead. Okay? Because the sum of the two have to be 90. Okay? Everybody got that one? All right. Now, we already talked about what the ecliptic is. It's a circle on the celestial sphere. By the way, someone mentioned this last time. Someone very observant. I said, what can you note about this? And almost the first thing out of someone's mouth was it's tilted. Okay? The Earth's axis is tilted. And this thing right here, it's going to be hard to tell here because of the way they measured it. There's 10 degrees, 20 degrees, right at 23 and a half degrees is the tilt of that axis. Okay? Now, does anyone know what the ramification of that is? Say again?
That's how we get our season.
That's exactly how we get our seasons. Right now, we're tilted toward the sun. The sun is somewhere, is past, how to say this best? We're tilted more toward the sun because our days are longer than our nights, but we're getting close to fall. What happens in just about a month? Say again? Yes, the fall equinox. Now, what would equinox mean?
90 days.
Equal nights. Not in German is night. I don't know what it is in other things, but equinox would be equal night and day. So you've got 12 hours of daylight, 12 hours of sunset. That's fall equinox. Over in March around the 21st, we have spring or vernal equinox. We'll be talking about these later. And what we had back around June the 21st was not equinox. Solstice. Okay. Now, what would that word mean? Solstice. I'm going to turn around. The sun is actually always, for us, appears to be in the southern hemisphere. Okay? And the summer solstice. Now, every day, and we're going to talk about this later, and I hate to do it now, but that name. Sol means sun.
Stis means still. Okay? What is happening, when they used to watch and pay attention to this kind of stuff, every day up before June 21st, the sun got a little higher on the local meridian. Every day got a little higher until one day it didn't get any higher, it stood still. And then after that, it started dropping every day. And in the winter, it's dropped, and it dropped, and it dropped. And it used to be, people feared that someday, sometime, it may keep dropping and we lose the sun and we all die freezing. But they were always very happy when it quit and stood still again, and that was called the winter solstice, and it started going back up again. And that's why they had big parties on the winter solstice. Okay? Now this is a little unfair to do, but from what I understand, it's probably pretty close to true. When Jesus was really born, remember there were shepherds out in the fields at night, right? Would they have been there around December 25th? So, pretty bad thing to do to your sheep and the shepherds too. It's cold, really cold then. So the odds are you celebrate the wrong time. Why? We wanted to make the celebration close to the winter solstice because everybody was celebrating anyway. Let's us celebrate them too. And unfortunately, we got everything overall. Okay, that at least is a theory. Because the dates are never given. But we do know that the shepherds wouldn't have been, I don't think, in the fields on December 25th. Never mind. That's a completely different issue. Okay. Now, so the ecliptic is a circle on the celestial sphere, and that circle is tipped at an angle of 23.5 degrees to the celestial equator. So celestial equator, wherever the celestial equator is, okay, that would be 90 degrees from our latitude, so it's going to be 90 degrees from that. So there's our celestial equator. So the ecliptic on summer solstice and winter solstice is tilted there. So all the time the ecliptic is tilted at that. That's the maximum in, and that's the 23.5 degrees. Okay? Now, what we were just talking about is shown in figure on page 361, this figure 47.2. When the ecliptic, which is where the sun is, crosses the celestial equator, that is they call it vernal or spring equinox. When it crosses again, it's the autumnal equinox, because there the sun is directly on the equator, 12 hours of sunlight, 12 hours of darkness. Okay? The winter solstice is when the sun is 23.5 degrees below the celestial equator, and the summer solstice is when it's 23.5 degrees above the celestial equator. And that's what makes our seasons. And that tilt is exactly, as Reuben said, that's what makes our seasons, that 23.5 degree tilt. Okay, good deal. Now, when the figure on 362, figure 47.3, the diurnal path, so that's the daily path of the sun across the sky at the summer solstice, it rises actually, it rises north of east, travels up above 23.5 degrees above the celestial equator, and sets north of west. Now I believe that, okay, but when we bought the house that we currently live in, it just was so nice that it faces almost due south. Just about exactly due south. So the back side of the house is facing almost exactly due east. And I drive my wife crazy by the fact that I open and close blinds every morning, every evening, depending on the time of year and stuff like this and what I do with them. Those facing north, I open them every day, let light in. So we don't have to turn on lights and waste electricity. Okay. Drives her nuts. She turns on lights anyway, probably. Okay. But in the summertime, I open the blinds such that blocking as much sun as possible. And in the wintertime, open them so it lets in as much sun as possible to take advantage of the warming of the sun or to block that. Okay, I'm cheap. Coral age squeals because I pinch them so hard, but never mind. Different story. Okay, so I noticed, and it was just such a pleasure to notice that sometime shortly after March the 21st, I started seeing when I opened that north-facing bathroom blind that I'd start getting a little bit of sun in. I said, oh yeah, the sun is rising south of, north of the celestial equator. North of due east, and setting south of due east. I said it back. South, okay. So anyway, and you can see that. Try it at home if you have a house that faces north, south, east, west. You'll see that's the case. And the sun rises, okay, I'll say it right, south of east in the wintertime and comes up less than by 23.5 degrees on winter solstice. The celestial equator is set south of west. So up there for a shorter period of time, and that's what makes our winter days shorter, our summer days longer. Now, I had in this class, probably 10 years ago or more, a woman who was originally from Kenya. And when we got to this phase, she said, that's why. I said, that's why what? She said, I wondered why in the world, because she grew up in Kenya, and guess where Kenya is? There's Kenya, right on the equator. And she thought her whole life that everywhere there were 12 hours of daylight and 12 hours of darkness, because it varied very little where she lived in Kenya. She came here, why are the days different lengths, And sure enough, that's why. The further north you go, the more the variation. My wife's family used to like to take pretty major vacations about once every 2 or 3 years. And one time, maybe twice, we went up to Alberta, Canada, and it was in June. And we thought the sun was never going to go down, We weren't so far off it didn't, but it was 10 or 11 o'clock, maybe 11, 9:30, 10 o'clock at night before the sun ever set, because we were so far north. Boy, those were long days. Long days. And that sun would come up and wake you up way too early. Okay. That's why. All right. Now, a couple of other terms. And these are one of the things that I found almost contradictory with what the book talked about, but they're not. They really fit together well. 2 terms. One is called declination. And you look at it, as described in figure 47.4, and that almost looks like what we were calling altitude before. Except that that's not what it's talking about. It's how far above or below the celestial equator something is. Not our horizon. That was altitude, above or below the celestial equator. So the thing shown here looks like it's about 50 degrees north of the celestial equator. Okay? Something down here would be so many degrees south of the celestial equator. That's what we call declination. And by the way, since the stars are all fixed out there, their declination doesn't change because compared to the celestial equator. Okay? So, let's move on from there. Now, remember before, and this is Ruben, when he was telling me he was a fire control technician, they dealt with altitude, and remember we talked about azimuth all the time because that's when they were doing the gunfire directives. Okay? That's the thing they used to measure that. Now, what did you use to measure by the due north or direction of the ship?
Yeah, due north.
Due north.
Figured out,
Yeah.
DY.
All right. And whereas we were talking about due south, so a little bit of difference there. But when we're talking about the celestial equator, we'd say right or left of somewhere. Well, you don't really have due north and south there. So what we use is vernal equinox, where the sun crosses the celestial equator on the 21st of March or thereabout. So that's what we measure, and what we call that is right ascension. There is probably some reason for that, but not a real clear one. Okay? So then we define an object by its right ascension and its declination. The objects will be there. Okay? So that's what we're going to do next in part B. We can now use the points and circles we've discussed thus far to do this. The declination is the angle above or below the celestial equator, and right ascension is the, and I was trying to see how they measure it here. We'll talk about this a little bit later. It's east or west of the plus or minus from the vernal equinox, where the celestial equator and the ecliptic cross in the spring. Okay. So positive is north of the celestial equator, negative is south of it, and subdivisions are usually degrees, minutes, and seconds apart. Now, the right ascension is, like we said, a little more complicated. The right ascension of an object is the angular distance measured along the celestial equator between the vernal equinox, that's always where we start, where the sun's ecliptic crosses the celestial equator in the springtime, okay, and the point on the equator, okay, got it. An hour circle is a great circle that passes through both celestial poles as well as the object itself. Okay, why did they throw that in? Because we measure right ascension in hours, not degrees. Okay? Bit bizarre, but true. Okay? The subdivision, now here's the other thing that's bizarre. Degrees, subdivision, a 60th of a degree is a minute, and a 60th of a angular minute is a second. An angular second, angular degrees. A 60th of an hour is a minute, and a 60th, but that's an hour circle minute. And so you have minutes and seconds both in degrees and in time, and they're not the same. So that's what we're going to look at next. Okay? Now, if you think about the celestial equator, and that's what things are measured from, how many degrees are all the way around the celestial equator? 360 degrees, right? Okay? How many hours does it take the sun to be at one point to the next point or around the celestial equator? 24 hours. So the ratio between the hours and the degrees is a ratio of 24 to 360, or 360 to 24. So right ascension is measured eastward from the vernal equinox. Okay? I guess that's why they call it right ascension. So the question, I'm going to erase this. I hate to because I'm going to use it again later, but let's erase it for now. And let's see, how many degrees of arc? Okay, now we know our ratio is 360 degrees of arc is equivalent to 24 hours of right ascension. RA is right ascension, ARC is arc. Okay?
So that produces a ratio. So it says how many degrees of arc are equivalent to 1 hour of right ascension. So let's do 360 degrees of arc is to 24 hours of right ascension. Let's reduce that and find out how many degrees of arc are equivalent to 1 hour of right ascension. Well, what can you divide into both 24 and 360? Say again? A little louder? Okay, someone's already done the whole division, and you got 4. Does everybody see that? Divide 360 by 24. Wait. Yeah, you get 4 on the nose, don't you? Okay. Do you? Let me see. Someone with a calculator.
365.
It's 15, isn't it? 15. I thought that was right. Okay. That's 15. 15 degrees of arc is 1 hour of right ascension. Okay? Now, someone was doing the next question. How many minutes of right ascension are equivalent to 1 degree of arc? So if we have, so number 4, the answer is 15 degrees of arc. Okay? Now, how many minutes of right ascension are equivalent to 1 degree of arc? Okay? Well, what we're looking for now is minutes of right ascension. This is minutes of right ascension would be equivalent to 1 degree of arc. That was what the question was, right? Yeah. Well, how many minutes of right ascension is 1 hour? 60 minutes is 1 hour. So 60 minutes of right ascension would be equivalent to 1 hour of right ascension. So how do we, if we divide 15 by 15, you get 1. What happens if you divide 60 by 15? Say again? That's your 4 minutes of right ascension. Okay? So there is the answer to number 5. How many minutes of right ascension are equivalent to 1 degree of arc? Okay? Now the next question. How many minutes of arc are equivalent to 1 minute of right ascension? So here we're going to 1 minute of right ascension. Now how many minutes of arc are in 1 degree of arc? 60. 60 minutes of arc are the same as 1 degree of arc. 60 minutes in a degree, just like the 60 minutes in an hour. And then what would that give you for how many minutes of arc are equivalent to 1 minute of right ascension? 4 will go into 60. Anybody? 15 minutes. You're right. 15 minutes of arc are equivalent to 1 minute of right ascension. That can almost seem a little confusing, but that's the questions they wanted to do. Okay? Everybody got it? Okay. You may want to take a little more time than I did to do that, but all right. Now, what we're going to do next, we do not have a celestial globe. Sorry about that, folks. But what we do have is what they call a star guide. Okay? This is the night sky between 40 and 50 degrees north latitude. That's at least on one side. The other side is, it's still north latitude, but it's what's on the southern side. Okay, so what we do here, even though it's printed this way, you turn it this way. So line up, this is the North Pole, by the way, right there. Okay? And here's sort of how you can tell that. Here is Ursa Minor, which is the little bear, which in that is the group of stars we call the Little Dipper. Over here is the Big Dipper. There it is. There's the handle. There's the cup. And when these two pointer stars are pointing straight to Polaris. Okay? So that's the North Star right there. Okay? Now, so when you line up down here, where is right ascension measured from? What date do we say? Right ascension is measured from the place where the ecliptic, which is this dotted circle here, crosses the celestial equator, which is the solid circle here. Okay? That is your vernal equinox. And by the way, it comes out being March 21st on here. Exactly. So, the question is, which stars are located at the following coordinates? They give the right ascension first, always measured from vernal equinox, where the celestial equator crosses the ecliptic. Right there, March 21st, down here. Okay? Right ascension is 6 hours and 43 minutes. Okay? But what you have to do here is, and maybe it would be better to hold it like this because you can read it better. Okay? There you lined it up. It's moved a little bit, but not far. Maybe I'll move that on that. Okay, you're moving. Well, I'm having trouble seeing it now. I believe it's to the right. I always start to do this backwards. So what did it say? 6 hours, 43 minutes. There's 1 hour, 2 hours, 3 hours, 4 hours, 5 hours, 6 hours, and 43 minutes. That's about 6 3/4. So I'm going to take this and move this way, 6 hours and about 3/4. You got to sort of estimate that. Okay? Now what date does that give you? That gives me June the 20, I'm going to say between 8 and 9. So I'm going to twist June 28 to 9 up here so I can line it up. Okay?
Between June 28th and 29th.
Say again?
But between June 28th and 29th.
Yeah, June 28th and 29th, somewhere right in there, right about there. Okay? Bring this up, and then what we have to do is determine declination. Now this is below the celestial equator, and that's why I like to hold it this way, because holding it the other way, it's backwards. Here's the celestial equator, there's due north, so south of the celestial equator, about 16 degrees. Now that's really hard to guess here, except that this is 90 degrees, there's 45, half of that would be 22, 16 would be a little bit less than that, so that's just about what we see here. There's a big bright star right there. Okay? Y'all probably can't see it, but I'll read it for you. Sirius. S-I-R-I-U-S. Sirius. Are you serious? No, not spelled that way. Okay. So there's your star name, Sirius. Now I just demonstrated that for you. One of you is going to try it. Now I'll help walk you through it, but who wants to do it first? There's plenty of stars and constellations, so speak up.
Hewitt. Okay, good deal. Okay. Where do we start measure our right ascension from? Actually, yeah, you need to go to this thing so you can. I find it easier to turn it over to this part, then you'll need to turn it back for another part. Okay, where do you measure your right ascension from? Anybody?
6 hours, 22 minutes.
Second?
6 hours, 22
Okay, yeah, but where do you measure it from? You have to know where to measure that from. The vernal equinox, which is when? March 21st. And that's also when, so no, you keep this down here and turn the wheel. March 21st. Yeah, you turn it right. Keep going, here's March. Okay. And it's also, that's where the ecliptic, which is a dotted circle, crosses celestial equator, which is the solid circle. So move that down so that's right on your thing. Yeah, twist, yeah. Oh, the other way. Yeah. March 21st. Keep going, keep going, keep going, keep going. March 21st. And sure enough, you're right where the celestial equator crosses the ecliptic, right? You see that? Okay. And how many? What? Right ascension? How much? 6 hours and 22 minutes. So that's just under 6.5 hours. So measure to the right. Here's the hours thing. 1, 2, 3, 4, 5, 6. 22 will be a little bit less than half. So that looks like about June the 3rd maybe? Okay, so turn June 23rd down to the whole. You'll think she planned this. June 23rd. Oh, you went past it, didn't you? That's 25th. Oh, yeah, there we go. About June 23rd. No, 23rd. Yeah, somewhere right around a little bit more. Right there, 23rd. Yeah. Okay? Now, but what's your declination? Say again?
-52.
Whoa, that's south of the celestial equator. Hey, before Sirius was right on, the thing. So you can't see that. So try turning this over, and that shows you something that's down there. But I still don't think we're far enough south. You have to read it backwards now. It may be here. I would say some star, let's just call it south of Columba. That's a constellation. We can't see the star because we don't have enough pictures on the thing here. So write for star name because you're way below the horizon. That would be some star south of Columba. 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 Yeah. Columba. Columba. Can't see it on here because it's too far south.
What's that called again? You got it right there.
Oh, this is called I call it a star chart. Okay? They call it the night sky.
I mean, I went to like Barnes and Noble or something.
Yeah, you can get one if you want to.
What did it call? You said I want to call it the right thing. That's all I'm saying.
Okay. Well, this one just calls it the night sky. I have another one that called it the Star and Planet Locator. That one's an Edmund Scientific, but it's almost torn up, so I went to this one. We happened to be in, I think, Yellowstone, and we were at one of the gift shops. I saw this, I went, hey, there's one, mine's tearing up. Oh, I think, fine. So we did. She controls the pocket. Okay, who wants to go next? All right, good deal. She makes a big bunch, by the way. All right, where do you start to measure right ascension?
March 21st.
March 21st. Line the hole. Line the hole up there. Yeah. Line the 2 holes up.
Wait, hold up. This is a whole
Too many moving parts, okay?
Alright, so one down here and then pull that one.
No. Hold them both down there. Yeah, just do that there. Okay. Hold your finger right over it. and do March 21st. Spin the wheel till you get to March 21st. Here's the wheel.
Oh,
Ah,
sorry, I got you.
got it. March 21st.
All right.
What's true about March 21st? Vernal equinox, which is what happens there? Ecliptic crosses the equator there. You see the ecliptic? That's the dotted line, and the equator is, yeah, there you're on it. Okay? 18 hours and 35 minutes, just over 18 and a half hours, right ascension. Okay? So you start counting the hours. 1, 2, you see this little triangle. 3, 4, okay. 6, 7, 8, 12, 13, 18 and a half will be about what day?
December 27th.
December 27th. Slide that down to your hole. Okay. This time we go up 38 degrees and 44 minutes from the celestial equator. So a little over a third of the way up. Is there a fairly bright star a third of the way up? From here to there. Yeah. What is it?
Vega.
Vega! V-E-G-A. Vega. Very good.
It was a good card, though.
What's that?
I said it was a good card.
Yes. You're right. Okay. Who's next? All right. Good deal. Thank you. All right. Where do we start? Oh, by the way, until I write on the board again, let's get some white on this side. Oh, sorry. Was that too much? All right. Where do you start to measure right ascension from? March 21st. So line that up. Okay. And is that where the celestial equator crosses the ecliptic? Absolutely. See that? Okay. And you measure how many hours right ascension? 5 hours and 12 minutes and just under 5 1/4. So measure here's 1 hour, 2 hours, 3, 4, 5 1/4. No, wait. Pick the date for it. About a quarter way between June, maybe June 8th. Okay, twist June 8th around under your string. Okay, and where do we go? Minus 8.5 degrees. It's not too far south. Okay, is there a pretty bright star there? Yeah, there he is. Rigel. R-I-G-E-L. Rigel. Okay. All right, good deal. Who's next? I can stay past 6. Oh, someone volunteers. Okay, good. All right. Somehow that gets volunteers to come out here. Okay. What's that? Rigel. R-I-G-E-L. Rigel. Okay. All right. Where do you start? Okay. Yeah. Start where? Where do you measure that from? March 21st. Okay. Yeah. Hold the screen so the circles line up. Okay. Twist this until you get to March 21st. Do about March 21st. Ecliptic. The dotted circle crosses the equator. Solid circle. There you're on, right? Okay. And from there we measure. Which one is it? 7 hours, 37 minutes? Okay. 7 hours to the right now. I mean, to the right essentially, which is this way. 1, 2, okay. And then about a little over halfway until you get to the next one. Just pick a date from there. No, here's the 8. So a little over halfway between 5 and 4 there. What's that? Huh? Okay, July 15th. That's going to be close. So twist July 15th down to here. Okay. Now you go up from the celestial equator, positive 5 degrees. Not very far above there. Here's the celestial equator. Circle that. You see a bright star somewhere close to that. Right. See right up there. See it? What's that star? Procyon. 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 Procyon or A-N? O-N. Procyon. Very good. Who's next? Brave souls. It's easy.
I
Oh,
knew
all
that.
right,
I was
good
like,
deal.
I knew you.
Oh, old man. Did I do that? Oh, I'm sorry. All right. Get out of this place. We'll knock something else over. All right. This is the last one on the stars. Where do you begin? All right, she's already there. March 21st. March 21st. Yeah, there you are, right where the equator crosses the ecliptic. Great, very good. And then you count 14 and just over half an hour. Right ascension is this way. There's one, yeah, not go. Okay, yeah, here's the first one, right? One, yeah. And a little over half an hour more. So 36 minutes. A little more. Toward 11. I mean, toward 9. It's just past half. What date do you give us? Oh, that's not too far. Let's say 26, maybe, 24. Okay, yeah. That just gives you a place to mark. And then what's your declination? That's the last one.
Negative 60 degrees.
Oh my goodness, that's way below the equator. So flip over and see if we can see anything there. And it's still, you have to look this way and you still can't get it. So it's something south of Centaurus. All we can say, something south of Centaurus. That's Centaurus. That's actually a constellation, not a star. Something south of Centaurus. That was another almost star. Okay, never mind. All right. We're going to do the same type thing for constellations now. These will be even easier. Okay, who wants to go next? Oh, good. Oh, you just did one, didn't you?
Yeah.
Huh? Okay. Let's let everybody have a shot. Okay? That's all we can. We're too big a class for everybody. Where do you begin?
March 21st.
Okay. What is true about March 21st?
Vernal.
Vernal equinox. And what's true about vernal equinox? Equator and the celestial equator and ecliptic crosses. Ah, you're right on it now. Is that around March 21st? Okay, good deal. And then you go how far?
11.
Okay, count 1, 2, yeah. Okay, and what date is that? Okay, September 3rd. Push that around to your extreme. Okay, and plus 50, more than halfway between the celestial equator and the North Star. You have more than, yeah, just a little over halfway. I believe it is. That's who? Leo Minor. Okay. What do you think Leo may stand for? The lion, and this must be the little lion. Okay. I don't know things about that one. So. Very good. Leo Minor. Leominor. Who's next? All right. Good deal. Okay. Where do you begin?
19.
Oh, where do you begin though?
The March 21st.
Okay.
Yeah,
So you
yeah.
switch around to your March 21st. Hold so they line up. Okay. March 21st.
I'll bring this one to the
Yeah, bring
screen.
that around to March 21st. And you bring those wheels on the.
When we did a NGF festival, we shot the gun. We had to watch the thing.
March 21st. What's true about March 21st?
the celestial equator, which is a solid circle across the ecliptic. Yeah, you're right there on that.
Okay.
Okay? And you measure how many hours right ascension?
19.
19. So start here, and there's your first one, there's one. Count however you want to. Yeah. No, don't move it. Just
Okay.
count around. Count. Just count.
Yeah, well, get back.
Oh, okay, got it.
All right, we got to count that.
Okay. 1, 2, 3. Those little arrows on there.
Oh, okay. And how many?
19. I think you got off somewhere because you see if this is right down here, that's going to be 12.
Right.
That would be 18. That would be 18. 19 would be one more. Okay, what date is that?
January 7th.
What a wonderful day! My birthday. January 7th. Okay. Yeah, okay, so twist January 7th, that round, yeah, so it's down there. All right, this must be a good one. Okay, and it says minus 25 degrees. That's 25 degrees south of the celestial equator, which is right there. Man, I can't see anything. So flip over and see if we get anything better on this side. Okay. Look at it this way. 25 degrees south. Might be, reckon that's Sagittarius?
Yeah.
Let's say it's Sagittarius. Okay, let me spell it for you. Sagittarius. Sagittarius. Okay. Say again?
That's my son.
Okay. Oh, that's your sign? Oh, excellent. Okay. I think that's mine too. When are you born?
December 1st.
First? Okay, I think that's the one before me. Okay. All right. So there's Sagittarius. Okay, who's next? Come on, be brave. We can stay. All right, good deal. Okay. Where do you begin? March 21st. Hold the holes, the string, hold the strings of the, right, let's hold. Twist your thing here as we get March 21st. This is pretty exciting stuff, isn't it? What's true about March 21st? Look at it, crosses the celestial equator. Right there. Not in trouble with the top. See it? Okay. And then you do how many hours? 3 hours. 3 hours. 1, 2, 3. They closest to that. 6. Okay, we're going to twist that around down there. Yeah, just push that until it's under the hole. Okay, and plus 20. That goes up just a little ways above the, see, this would be 45 halfway, and after that would be about 20. All right, constellation is that. Let's just call it Perseus. Okay, let's call it Perseus. It may not be exact, but we'll call it Perseus. 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 Remember, he was some Greek.
Say it again.
Again. Perseus.
P-E-R.
And he was chasing, so yeah, Perseus. All right. Who's next? All right, good deal. Okay. And where and how do you begin? Again? Yeah, but sorry, where do you start? Okay, 21st start. Okay. All right, line up the holes. all the time. Twist. Yeah. What's true about that? The celestial equator, which is this circle, crosses the ecliptic, which is the dotted circle. Yeah, you're right on. And then how many hours by ascension? Oh, you this one. Okay, 1 hour. You count your hours. There's the first hour right there. Okay. What day is that? It just gives like around 6. Okay, twist April 6th, so it's on that screen. Okay, and then we go 60 degrees north. 2/3 of the way north. What do you do? Okay, yes, I don't know how to pronounce it. I'll give it my best shot. See it again. No, I just saw it. Where did it go? Cassiopeia, or Cassiopeia, one or the other. Cassiopeia. Cassiopeia or Cassiopeia. Now, I usually can't pick it out, but the closest I can come, it looks like a W. I never figured out why Cassiopeia should look like a W until the guy at the planetarium explained, turn it a little differently, and it looks like a throne or a chair. Okay? And the story was Cassiopeia either fell in love, or one of the gods or minor gods or something fell in love with her, but they couldn't, because she was, real and he was, or whatever. But she was very beautiful. But whoever the father or somebody was decided to chain her to the chair so that she could never marry whoever his son was, or whatever. It was some sort of weird story like that, and that's why it's a chair or a throne. I thought it was a W. I thought he was former president or something. No, not that. Okay. All right. So there was that one. Next to the last one. Come on. You've already done one, haven't you? Come on, someone who hasn't done one. I've got till 6. All right, good deal. Okay. Now, where do you start? Okay, so turn it, hold your string so between the holes there, and turn it to March 21st, which is right on the string. Yeah, pretty close. I'll turn it a little bit this way. Okay. Okay. So you're at March 19th on that side. Okay, a little bit more. A little bit, no, this way. A little bit more. A little bit more. There you go. And what's there? The equator, celestial equator, which is that circle, crosses the ecliptic, which is the dotted circle there. Yes, you're right on the vernal equinox. Okay? Now you count 13 hours that way. So there's your hours. 1, 2, 7, 8, 9, 13. 11, 12, 13 right there, and see what date that is. 2nd, it looks like. Okay, that's October 2nd. So twist October 2nd down so it's on the string. Couple more. Right about there. Maybe one more. Okay. And now you go minus 50. You can't get 50 below there, so let's turn over and see if we get anything there. This way, yeah. Let's see. Let's just call it Centaurus. There's the constellation Centaurus. 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 Last one! I think, okay, good deal.
I thought you were dropping the raise your hand, but you were pushing up your hand. Yeah. All right, where do you begin? March 21st.
There's two centrolysis?
What's that?
No, the other one said something south of centrolysis. South of. This one looks like it looks like.
Yes, that's where the ecliptic, which is dotted circle crosses the celestial equator. That's a solid circle. You're right on it. Perfect.
Good job.
Okay, and then how many hours? No, okay, 7. 7 hours, last one. Okay, here's your hours. 1, 2, 3. Okay, and what date is that on? July 4th. Okay, twist July 4th until it's on your screen. All the other way. There you are. And how many? Minus 40. You can't see minus 40 there, so let's flip it over. Let's see, minus 40. That looks like it could be maybe. Yeah, let's call it Pupus. P-U-P-P-I-S. Okay? Pupus, I don't know what you call it.
B as in boy or P?
P-U-P-P-I-S. All right, good deal. Now, I'm going to do some of this part, but I think you can probably follow it okay. It says, on the ecliptic, locate the position of the sun on June 21st. Okay? I don't really think you really need this, but I will do it June 21st. I'll line this up right there on June 21st, but I'm not on June 21st yet. I need to twist this a little bit to get to June 21st. Right there. Okay. Now, there is my ecliptic, the dotted circle up here. There's celestial equator down there. Can anyone tell me how many degrees are between the ecliptic and the celestial equator on June 21st? And a half. 23.5 degrees. That's not part of the question, but just wanted to know. Now it says, does the sun rise exactly in the east on this day? I'm guessing you probably know the answer to that, but what I'm going to do is take the string this time and twist it around here until to the east, until you see the sun rising. Okay, there's some way to do this. How would I do that? Oh, okay. I guess what? Okay, I'm sorry, I twisted the wrong thing. Twist the circle around. Now, I need to be on the ecliptic, and the ecliptic there is just in, I guess this is the Milky Way that goes through there. You see, this is a little tedious, so sorry about this. And there is the thing. So I'm right between those two dashes, right there of the ecliptic. So I'm going to keep my eye on those two dashes and see when that rises. Right about there. Does the sunrise due east? No. It's, I just lost it. I had it, my eyes on it. Somewhere up here. It rises north of east. No, it rises north of east. And we talked about that before. Remember the sun coming in the blinds? It comes through north of east. So, number 10, no, it rises north of east. Okay. Now. what it says next is rotate the globe, which I'll be rotating the circle here, sort of, and count how many right ascension hours the circle lies between the rising and setting points of the sun, and estimate to the nearest 15 minutes the amount of sun is above the horizon on June 21st. That's tedious, but somewhere here I thought I had my watch. I'm trying not to go over. How are we doing on time?
It's like 5:13.
It's what?
5:13.
5:13. We've got about 30 minutes to go. Okay? Now what I have to do is,
So we're doing the second part of number 10 right here.
what's that?
We're doing this part of number 10, rotate the globe.
Okay, it just says, does the sun rise exactly east on that day? No, it rises north of east.
Yeah, now we're on this one.
Yeah, now we're on the thing underneath that. Now, what I have to do here is figure what time the sun actually rises then. Okay? I'm estimating, and I'm going to say about, here it says really close to 4:30. 4:30 a.m. Now, this isn't our time. This is 40 to 50 degrees north. So this is well north of us. We're 33 degrees. So it wouldn't rise at 4:30 here, but where we are on this thing is 4:30. So it rises at 4:30 a.m. You can write that somewhere down there. Oh, man. Okay. I'll clear this out of the way so it won't be confusing. Okay. So we'll say 4:30 a.m. Okay. That's sort of going to be unnecessary in a minute, but you'll see why. Okay, now I need to rotate the sun. I need to find it again. Oh, I know what I could have done. Okay. Until June 21st is just setting. Okay. June 21st is between these two dashes here. So let me twist this on around a little bit further. Tedious. Right before it sets. Oh, it's coming close. It's dusk there. I think it's setting right there. And that looks like that's about 7:30 p.m. Just going to round it to 7:30 p.m. Now, let's see if our naval scholar here can give me 7:30 in military time.
That'll be 1930.
1930, that's 7:30 p.m. Okay? The question then is,
You're just like putting it right there. And it's under this one. It's right now.
yeah, we're
We're
number,
just like putting the times down.
okay. Okay. Okay, where you write the answer to this, by the way, this is estimating to the nearest 15 minutes, the time is above the horizon. And did you do the calculation? What would that be? Subtract? Anybody? Pretty easy math. 15 hours. So we'll just say 15 hours. Now remember, this is further north than where we are. Where's my globe? 40 to 50 degrees north. 45. Globe. 40 to 50 degrees north is up there. It's just about, oh no, let's just say Boston, Massachusetts or somewhere. Way up there, okay? So this is not us. This is there. So 15 hours of daylight. Now where do you fill that in? Flip the page, and it says here, relative amounts of daylight and darkness for your latitude at different times of the year. Okay? We're not doing our latitude. We're doing this 40 to 50 degrees. So the first thing we've got to do is find the declination. That's not SEC, it's DEC.
declination of the sun. What do we find it to be? On June 21st? Second? 23.5 degrees. So you can either do 23.5 degrees or 23 degrees 30 minutes. However you want to say that. Declination of the sun, 23.5 degrees. You can either do plus or you can do north. One or the other. And what was our just calculated number of hours of daylight? 15 hours of daylight. So how could you figure how many hours of darkness? Subtract it from 24, and what do you get? 9 hours of darkness. There you got it. Okay? Now we're going to do the same thing for December 21st. So what I'm going to do is get December 21st right here. Whoops, I went the wrong way. December 21st right here on my thing. I really don't need to. Yeah, I do. December 21st. Does anyone want to tell me what December 21st is? Awfully close to it. Winter solstice. So what's the declination of the sun on winter solstice? Say again? Negative 23.5 degrees, negative 23:30, 23.5 degrees south, 23:30 south, however you want to say it. That's the declination of the sun on the winter solstice. Now this is a big boo-hiss. It doesn't even show on this side. So let's go over here and see if I can find it here. There we have it. Winter solstice. Oops, on the wrong side. Okay. Oh, that's a little. Oh, it's right there near this right angle signal near M8. So we've got to twist it around till. M8, that little right angle. Let's see if they have that over here. Sun rising. I can't see it at all in here. So I'm going to have to use this side. Okay. Now I've lost. Okay. This is why I'm not making y'all do it, because this is really tedious. Okay. December 21st is decorate. Okay. I was on the wrong place anyway. Okay, it's just on this side of that line. So I see it now. I've got to turn the right direction here. Okay, here we go. I think I'm heading the right direction now. Okay, the sun is going to rise on that day right about, let's call it for funsies, I think my hours are off. Sun rising 7:30 a.m. 7:30 a.m. Okay. And what time does it set? Let's twist this around so it just about is going beneath the horizon here into night, right about there, and that's going to be, let's just for fun call it 4:30 p.m. 4:30 p.m. And what's that? And I didn't write down. 4:30 p.m. is what time military? 16:30. And what time did it rise? I didn't write it down. Second? 7:30. Okay. How many hours of daylight? 9 hours of daylight. How many hours of darkness? Say again? 15. I thought it was 15. Just exactly very close to the reverse of what the other was. Okay? Did you get declination of the sun that day? December 21st? Yeah, y'all got it. Negative 23.5, negative 2330, 23.5 south, 23 negative, yeah, whatever you want to call it. Okay, March 21st. What's the declination of the sun? Yes.
Okay, so what was the number of hours of daylight?
Okay, for December 21st? Okay, December 21st, number of hours of daylight was 9. December 21st. What's the number of hours of darkness? 15. Got it. Okay, March 21st. What's the declination of the sun? Is what?
It's the vernal equinox.
Yes. So what's the declination of the sun that day?
0.
0. The ecliptic is right on the celestial equator. Ecliptic is where the sun is. So it's 0 degrees.
So would it be 12 and 12?
Say again?
Would it be 12 and 12?
Yay, listen to that. 12 hours of daylight, 12 hours of darkness. I could do it on here, but she's already figured it out. Okay? Now we're moving up to, goodness gracious, is it cold there? Altegard, Norway. Okay? Latitude 70 degrees north. I'm losing my voice. Okay? On June 21st, what do you think the declination of the sun, that's again DEC, not SEC, of the sun? On June 21st. Has the sun moved any? No. Has our celestial equator moved any? No. So what's the declination of the sun? Really? June 21st? North 23 and a half, or plus 23 and a half, 2330, whatever you want to call it. Declination of sun doesn't change. Okay.
For all of them?
Yeah. For all those, you can put those 3 declinations of the sun. You're absolutely right.
So,
June 21st is going to be plus 2330, or 23 degrees and a half, 23 and a half degrees north. However you want to say it, just make sure I understand, you understand what it is.
So all June 21st, you can put 23:30.
Yeah. For all 3 of those, the declination of the sun on June 21st is 23 and a half degrees north, or 2330 north, or positive 2330, or 23 and a half, whatever. Okay. Now, we have to figure out the number of daylight hours in Altegard, Norway on June 21st. Now, we can't use this. So I think what I'll have to do is go back to my drawing here. Okay, I'm going to erase all the ink. And we're going to have to do our globe down here. Okay. And here we are. Now this time we've got on a pretty heavy coat. Okay. So here we are in a heavy coat because we're 70 degrees north of the equator. Does that look like about 70 degrees to you? 70 degrees north of the equator. Okay. Let's get our horizon in here. Here's our southern horizon. Here's our northern horizon. Okay? Now, our zenith is directly overhead. That's our Z. And let's do the celestial sphere. Something like that. Not a very pretty one, but we'll live with it. And our celestial equator is somewhere about like this. 70 degrees north is our zenith. This is on June 21st, okay? And where is this going to work? Maybe not. And 23 and a half, this isn't going to tell us that, really. Sorry. I think we just have to figure this out, okay? Altegard, Norway. 70 degrees north. Okay?
They don't show altogether, but it's about as far north as you can get to Norway. 70 degrees north. Guess what circle that's above? Anyone read that? Arctic Circle. Okay? Anyone know what the Arctic Circle is? It's cold up there, you're right, that's why we put a coat on. Okay? Arctic Circle there. Okay? We're above that, up here. Near North Cape, or Hammer, whatever you call that. Okay? We're above that. Now, what's true about that? The sun never sets. So how many hours of daylight do you have?
24.
24. How many hours of darkness?
0.
0. Now, here's the other thing about it. The sun never gets very high either. It's the highest over here, but it's the lowest over here. It doesn't get very high at all. It just stays right close to the horizon, above the horizon. That's what it is. So 24 hours of daylight, 0 hours of darkness.
So
How about?
Is it just like dusky there all the time?
Yeah, it's kind of like dusk, or a little bit better than that most of the time. A little bit brighter at noon and really dusky at midnight. Okay? All right. December 21st, declination of the sun? Negative 23 and a half. Okay? And this one I think I will draw on here, because if that's 70, you see, 23 and a half would be down there. There's the sun in Altegard, Norway, and guess what? That's at noon. Never rises. It's always above the horizon on December 21st. That's the noon declination of the sun, and it's below the horizon by, what, 7 degrees, something like that. Yeah. Yeah, 7 degrees. Okay, so how many hours of daylight? 0. How many hours of darkness? 24. All right, March 21st. What's the declination of the sun? 0 degrees. What is the number of daylight hours? 12, and even in Altegard, Norway, even on the North Pole, even on the South Pole, everywhere on the globe, it's equinox. Equal day, equal night. Right? All right. Now let's go down to Quito, Ecuador. Okay? It's right on the equator, latitude 0. What's the declination of the sun on June 21st? Plus 23 and a half. On December 21st? Minus 23 and a half. On March 21st? 0. Now, how many hours of daylight do you think you would have on June 21st? On Quito, Ecuador? 12. You're right on the equator. How many hours of darkness?
12.
How many hours on December 21st?
12.
How many of darkness?
12.
How many on March 21st?
12.
You're right. And darkness? 12. You got it. Really good, folks. Make sense? Okay, that's why the people who live near the equator don't realize we have longer days and nights as the year goes around. Okay, how are we doing on time? Oh, there it is. Oh, yeah, we can do it. Or we can proceed. All right, we need to turn back a page. This is a place where we sometimes miss 2 questions, and I'm glad y'all reminded me to turn back a page and get number 11 done. 11 says, calculate the altitude of the sun in degrees over the southern horizon at noon on June 21st for an observer at latitude plus 40. Woo. Okay, so let's take this one step at a time. So what I think I'll do is erase part of what I've got here.
Okay. I could take off the coat, but I'm not going to. It's pretty cold up there too, so. All right. Now, calculate the altitude of the sun in degrees over the southern horizon at noon on June 21st for an observer at latitude 40 degrees north. So 40 degrees north is going to be just under halfway, right? So I'm going to estimate that to be right about there. So if this is 40 degrees north, then this will be 40 degrees north. North is the celestial equator. This is celestial equator. That's our zenith. Okay? Now, you tell me what the declination of the sun is, and what the declination of the sun measure? Is 23.5 above what? Celestial equator. So we're going to do 23.5 degrees above that. That's going to be just over halfway here. So here's 23 degrees, 30 minutes north of the celestial equator. That's where the sun is. Oops, the sun. Okay. I put a star there. That's not a star. It's a sun. Well, the sun is a star, so never mind. Okay. All right. So what we want to do is the altitude of the sun in degrees over the southern horizon at noon on that day. Here's the southern horizon down here. Now first you need to know how far the celestial equator is above the southern horizon. What would that be? 50 degrees. Perfect. Y'all are good. Okay? And then the sun is another 23.5 north of that, so what would that be? 73 degrees, 30 minutes. That is the altitude of the sun above the southern horizon at noon if you're at 40 degrees noon. Very good. Now repeat for December the 21st. Okay, what is the declination of the sun on that day? Negative 23. Okay, so let me get some of this out of the way. Negative 23.5. That's going to be almost half of this. So this will be 23 degrees, 30 minutes below the celestial. This is on 21 December. Okay? So what will be the altitude of the sun above the southern horizon that day? How will you get it? Second? Anybody? I can't hear. Someone's saying it right. What? Go ahead. Be brave. Second? Oh, okay. What we do is subtract this because you're below the celestial equator. So I'm not going to do 50. I'm going to do 49 degrees, 60 minutes. Now, why would I do that? So I don't have to carry. Okay? Y'all didn't like carrying when you did subtraction, did you? I didn't either. So let's make it 49 degrees, 60 minutes. Isn't that 50 degrees? Okay? And then subtract from that 23 degrees, 30 minutes. And what do you get? 26 degrees, 30 minutes. So there's the declination of the, the altitude of the sun in degrees. You see it right there. When you're at 40 degrees north. Perfect. Okay, how are we doing?
Turn right.
Say again?
Turn right.
Not quite. Okay. So, let's go down to 13 on page 366. Aristophanes, oh, what a name, who lived in the 2nd century BC, was a Renaissance man way before the Renaissance, before his time. He was an astronomer, a geographer, a historian, a mathematician, has my heart, and a poet. Okay? With such a diverse background, it is not surprising that he was the director of the Great Library of Alexandria. That was in Egypt, by the way. That was the greatest center of learning at that time. This was 2nd century BC. Okay. 2nd century BC, the Great Library was there. Unfortunately, it didn't last very many centuries AD. Does anyone remember what happened? Yes. By whom? Does anyone remember? Okay, I think it was the Crusaders. Because these were pagan books. Well, they didn't understand. They didn't read very well. So they thought they must all be pagan. So they burned it to the ground. Now, the good news was much of it had been copied and hauled off to Baghdad and other places in the Muslim empires. They kept the learning alive while Europe went to the Dark Ages. And it was only afterwards, well afterwards, that the Enlightenment or the Renaissance came back to Europe. So that's history. That's not physical science, is it? In one of the scrolls in the library, Aristophanes read that at noon on June 21st, in the southern frontier outpost of Syene, Egypt, near the first cataract of the Nile, I think that's something like a waterfall type thing, of the Nile, obelisk cast no shadows on noon on June 21st. As noon approached, the shadows of the temple columns grew shorter and shorter until noon they completely disappeared all the way around the temples. Okay? Reportedly, a reflection of the sun could be seen at the bottom of a well. On June 21st at Syene, this means the sun was directly, absolutely directly overhead. Guess where the latitude of Syene would be? Second? No, on the equator, that would have only been on the vernal, well, yeah. Say again?
Oh, minus 20.
It would have been, the sun would have been 23.5 degrees north of the equator. Slip over here to Egypt, and sure enough, there is the Nile River in southern Egypt. Now, it probably didn't have the same boundaries as today. There is, just below, north of that is the Aswan Dam, which is a huge dam they put on the Nile, and that would have been very near the first cataract, because that's where you get enough fall. Anything above that, and it's going to be too flat, you wouldn't put a dam there. Okay, so that's sure enough, and that is on this line that we call we're going to talk about this in the next slide, the Tropic of Cancer. Below 23.5 degrees is the Tropic of Capricorn. Exactly. So we call anything in between there the tropics. They're close to the equator, but not exactly on it. But they can be things on it. But that on June 21st, that is where the sun will be. The ecliptic, that's the maximum point. So sure enough, that would be 23.5 degrees north. 23 degrees, 30 minutes north. Okay?
So that's the answer to number 13.
Okay. Used to determine the latitude of Syene, 23 degrees, 30 minutes north, or plus 23, 30, 23.5, however you want to call it. Okay, how are we doing now?
3 minutes.
3 minutes. You think we have time to do 14? No, yeah. 4. Okay. What's that?
We have time to do 15 and 16.
Okay. Now, I don't have, does anyone have on your phones or something like that? If not, I have a locator thing that, wait, that's not it. Here we go. I have something they gave me at the Birmingham Southern College. So this probably won't be quite right today, but let's answer it. When is Mercury visible in a dark sky? Okay. Now, what we're talking about now is, oh, wait. Okay. Since we don't have this for this month, let's just use October. No, let's use November. And it doesn't really matter what you use. It's visible late November in the early morning skies. So put just before sunrise. Now, why do we know it's always either going to be just before or just after? Where is Mercury? It's right close to the sun. So wherever the sun is, Mercury's going right with it. Now, sometimes it's below the horizon and we won't see it. Sometimes it's just above. But it could be just above in the morning or just above in the evening. Sometimes neither. This time, let's just do just, what did I just say? Just before sunrise.
Venus will be.
Second?
So Venus will be just after sunrise.
Okay, let's do Venus. Now that's next. Venus, I'm going to use the stuff that she gave us. It would be also be just before sunrise. Okay? Just happens to be just before sunrise too. They don't matter, but again, Venus is closer to the sun than us, so it's always going to be near sunrise or sunset. What do they call Venus? The what? Yes, you probably have heard it. The morning star or the evening star, because it's the brightest thing in the sky at night except for the moon. And it's always going to be early morning or late or just before, after sunset. Now, estimate how long each is visible in the dark sky. Okay, here's all you have to put. Mercury, just a few minutes. Don't expect it to be up there very long. I have never known if I've ever seen Mercury, because it's there so seldom, and quite often you can't even see it. Venus will be just a few hours, but it'll never be very long, like won't go past midnight or before midnight, depending on what time. So it's just going to be a few hours.
Okay,
Mercury, only a few minutes.
We will start.
We'll go back and do number 14.
Number 14.
That's all we've got left to do. So what we'll do next time is, at the very beginning of class, we'll do number 14.
Okay.
Then we'll pick up and go with chapter 15. And if we finish 15 before 3 o'clock, wait, is it 3:15? Because the last 30 minutes in the test, that's going to be 5:15 to 5:45. So before 3:15, if we finish the chapter before 3:15, we'll have the lab on chapter 15.
So what is our test on?
On chapter 14.
Okay.
Are you going to have the PowerPoints up though, since the test is Tuesday?
I'll try to get those up
So they
by
can
then.
watch, so they can look at them.
Yeah, I'll try to do that. All right, good deal. Thank you so much. Oh, yeah.
Have a nice weekend, Dr. Fallon.
Huh?
Have a nice weekend.
Okay, you too. Thank you. Yes, sir. Can I go on and close this up?